welcome to this tutorial. Just a bit of housekeeping to start with. I'll be giving an in-person presentation to start, and then there'll be two following virtual presentations from Wenjing Wang and Shuyu Wang. And I think we can make this pretty interactive. So welcome questions during the tutorial to clarify anything, both for those online as well as in the room. So please do raise your hand if you have questions. Wenjing, if you can help just coordinate questions online, that would be great to make sure I don't miss anything, because I can't see the Zoom screen right now.
Yeah.
Great. So yeah, welcome to this tutorial. Thanks for attending, and it's great to be back in person. We've held workshops at CVPR and ICCV for several years, and the last few obviously have been majority remote, so it's really good to be back in person. And this is a growing research community. There's a lot of interest in both video-based monitoring, but also remote monitoring through other modalities. And so it's really, really exciting to sort of keep that momentum up. I'm going to be starting by presenting on machine learning approaches for remote measurement, particularly from facial videos, although many of the techniques can be applied to other regions of the body because they're either PPG-based or motion-based. And so this is not necessarily exclusive just to facial analysis. I'm going to talk about the principles underlying measurement from optical sensors, and then talk about some of the challenges and opportunities with data. Then I'll discuss some of the modeling approaches that are popular and where the community's been moving over the last few years. I'll talk a little bit about optimization, and then finally evaluation, and kind of hopefully give an idea of where the state of the art lies. There's been growing interest, as I mentioned, and particularly over the last 10 years, really a sort of exponential increase in publications on these topics. And what's particularly exciting is to see the range of applications. So the majority have focused on PPG, photoplasmography, but there's growing amounts of research, particularly in oxygen saturation as well, and blood pressure, which is a challenging topic for sure, but I think there's some meaningful progress which has been made. I'll talk about some of these signals, but there's also opportunities, hopefully in things that are not on this list.
Hi, Daniel.
Yep.
You need to share your screen because we have online audience.
Oh, you can't see it? Oh,
no, we can't see that. No.
Sorry, I thought I'd share that. Just a second. Okay.
Yeah, now we can see your screen. Yeah, great. Okay, yeah, cool.
I should know this. Does anyone know the shortcut to go full screen from Chrome?
Yeah, you are in the full screen mode. That's good.
Let's try that. Can you still see the screen, Wenjing?
Yeah, we can see the screen. Yeah.
Yeah, okay, sounds good. Cool. And I won't have too much time to sort of motivate this, because I want to focus mostly on methods and data. But there are, I think, a lot of statistics that reinforce the fact that cardiovascular disease and other concerns are massive in scope in terms of the amount of people they affect and the impact they have on life expectancy. So there are many other statistics that we could bring onto these slides to kind of motivate why we would want to make remote monitoring more accessible for people, both in clinical settings, but also in consumer settings. And it's exciting to see some of this technology start to become available on consumer devices at a larger scale. This is an example of the Google Fit app, which does video-based PPG, in this case, contact-based from the fingertip. So I'm going to start off by talking about the principles, and I'm going to be focusing not on the images specifically. I'm going to be talking mostly about RGB sensing, but in this presentation, I'll be really talking about the methods, the data, and how we extract vital signs from those images. So of course, there are many factors related to the imager itself that can impact performance, the quality of the image sensor, the resolution, the frame rate, all of that. But I won't be talking about those in this presentation as much as focusing on the algorithms that we use to extract the measurements. So RGB cameras pick up typically visual and some near infrared information, and those wavelengths of light penetrate into the surface of the skin, and then light that's reflected back can be used to measure the blood volume pulse, but also reflected light captures body motions, which can be used to extract respiration or the ballistocardiogram. And so when we think about cameras as a measurement tool for physiological signals, the nice thing is that they have a range of capabilities. So that's something that we'll look to leverage in the methods that we design. I will be talking a lot about photoplethysmography because that is, as I mentioned, kind of the dominant area of research, let's say, and that is used to extract the pulsatile component of the blood volume pulse through light reflected from the body. But it can also be used to extract things like blood oxygen saturation and other composition types of variables. And many of the principles that apply to measuring PPG from a video can be applied to measuring respiration or other signals from a video. And then from the PPG signal, we may be able to derive other things like blood pressure, or at least approximations to those variables. This slide, I tried to separate kind of the things on the left-hand side, which have been shown to be sort of somewhat reliably measured by just a camera. Of course, depending on the application context, that will impact the accuracy or performance of those algorithms. But in principle, under good conditions, where you have a subject in good lighting conditions with little motion, I think we can say that we can design algorithms to measure heart rate, HRV, respiration, oxygen saturation if the illumination conditions are known, and AFib. There's little question whether we can measure those. It's just a case of how robustly can we promote those algorithms. On the right-hand side are things that eventually we would like to be able to measure just from RGB, but still there are, I think, fundamental questions about how accurately we can measure them. So there's a range of work, particularly on blood pressure, showing performance kind of ranging from extremely good to quite poor. And that's just because from PPG, there's not necessarily a very clear mapping to extract features from the PPG that predict blood pressure. And then temperature, glucose, hydration, electrodermal response, like those are all, there's very little work at this stage, I would say, from a visual spectrum. When we think about building algorithms, it's nice to start with a somewhat principled approach, and Wenjing has done a lot of work to kind of really ground these algorithms in physical principles that we can leverage. And the dichromatic reflection model is one way that we can model what the camera sees is related to the physiological change in the body. So we see here represents the RGB signal that the camera is measuring, and that is a function of the illumination in the environment, the specular and diffuse reflection from the skin, and then quantization error from the camera itself. But this gives us a set of equations that we can use to sort of justify that both the PPG from can be measured from a camera, but also first and second order derivatives of that signal should be possible to be captured from that device. And this video just gives a demonstration of measurement from a couple of different videos, and you can see close alignment between the PPG waveform and the signal extracted from the video, which is the white line. And that can be applied to as RGB videos and also infrared videos in case, for example, you're operating in low light conditions. That might be the case if someone's driving, or if there's a baby monitor that's operating in the dark. But for machine learning approaches, of course, one of the key considerations is the data that we use to train these algorithms. And how do we obtain that data? How do we synchronize it so that we have video frames and labels that can be used to train a model? And then how do we make sure that that data is representative of the conditions that we want to deploy in? And there's been great work across this community building data sets. There's a few listed here, but there's a larger set of data sets that are available publicly for benchmarking algorithms. And these are extremely valuable, but they are a pretty limited resource. So most of these data sets contain between 30 and 100 subjects, maybe slightly more. They're collected typically in one illumination condition in one room. So you can see examples here that the UVFC data is collected with a white background in an indoor illumination. There are other data sets with slightly more complex backgrounds or slightly darker lighting conditions, but when it comes to within data set training and testing, we often find that models are overfit to the conditions that data was collected in. And so we can do cross data set evaluation, but we are still limited by the amount of the size and diversity of these data sets. This table here just shows a larger set, and there are a few data sets that have become available since I created this table over the past 12 months or so. So there's a slightly longer list, but as you can see, the number of subjects and number of videos is fairly small, with the exception of a couple of fairly impressive data sets, BP40 and VIPL, which contain larger numbers of videos. But when it comes to practice, it's not just the size of these data sets that matter, it's how well the videos and ground truth signals are synchronized. Particularly when it comes to training neural models, we need to make sure that we can align labels with videos, not just average heart rate, but actually the full PPG waveform or respiration waveform, whatever signal we're aiming to recover. One other thing to say is some of these data sets contain multimodal ground truth signals. So again, VIPL is a good example of having PPG average heart rate as well as SpO2. There are some data sets with PPG and ECG, which gives us a more reliable ground truth signal for evaluating heart rate. And then some data sets that have electrodermal activity as well, which is quite exciting to see kind of a broader range of these signals within the same data set, so we can evaluate multiple signals at the same time. However, I think, as we've seen from those existing data sets, like we probably won't ever have, or at least in the near term, extremely large publicly available video data sets with high quality ground truth. And so I think there are some opportunities in generative AI and synthetics for us to hopefully be able to do intelligent data augmentation or create data sets from scratch. And synthetics is one thing that I think is pretty promising, given the fact that we have avatars and graphics models which fairly elaborately capture how light interacts with the body. And those models have been created primarily for things like filmmaking and computer games, but we can leverage that technology to create data sets that mimic at least the behavior in the real world. This video here just shows an example of some work from Tadas Bultrashaitis' team at Microsoft. And you can see kind of how, I'd say these are still pretty impressive renderings where we can model subsurface scattering of light in the skin. We can synthesize motion due to respiration. We can also synthesize lighting changes in the environment, facial expressions, and things like that. And one thing synthetics gives us that we often can't get from lab collected data sets is very high quality ground truth signals, not just about the physiological signals at play, but also things like skin segmentation and motions of the body. So precise down to the pixel level. So I think this is an area that I would like to see explored more deeply, because this is once a pipeline is built to be able to render videos, it can scale to very large scales. And as mentioned, we get that high quality ground truth, which allows us to train models that can do very precise, for example, skin segmentation, at the same time as training to predict the PPG or respiration. So that's purely synthetic data, but there are also data augmentation approaches that we can use to make the most of the real data that we have. Because we're interested in this case at looking at temporal signals in almost all cases, perhaps with the exception of blood oxygenation, where you might possibly be able to do that from a set of static images eventually. In this case, we want to recover PPG, respiration, these types of temporal signals from a video. Augmentation in the temporal domain is particularly attractive. And this is something that I would say has been less explored in other areas of computer vision, because many of those tasks don't involve recovering periodic signals. But in our tasks in physiological measurement, we often are looking for both temporal and periodic information. So in this example here on the left, you can see examples of motion augmentation, where we have videos from the UBFC dataset, which are not augmented. So on the top row, you see videos of subjects in that dataset with a pseudo PPG signal. And then below, you see examples of those videos augmented using a generative AI algorithm. So it's using the driving frames from a set of other videos to create motion of those subjects. And what we can see is that the PPG signal is still present within those augmented videos. So can we use these data for training an algorithm that is more motion robust, for example? We can also do things that are perhaps simpler than that by just augmenting the speed of a video. So we know that if we downsample a video by half, so we remove every other frame, we are essentially doubling the speed of the heart rate of the person in that video, right? Because we've removed every other frame. And so now to someone viewing that video at the same frame rate as the original video, it would appear that the heart rate has been doubled. And so that's a simple augmentation technique that can be useful for creating models that preserve frequency information more robustly. And I'll show some examples of that later in the presentation. We can also do augmentations that are more common in other areas of computer vision, like spatial augmentation. So this might involve cropping, rotation, adding color jitter or other things like that. But those augmentations, while helping with robustness to the position of the subject and things like that, may not be very specifically useful for extracting physiological information. So I would love to see the community invest more in augmentations that are specific to the types of signals we're trying to recover, which are temporal and periodic. Just as a side note, the SCAMPS data set that I showed earlier is available to download here. I'll post a link to this slide deck in the chat after the presentation so folks can access it. And then another data set that we released at the University of Washington recently is the MMPD data set. One of the limitations of existing data that's publicly available is a relatively strong bias towards lighter skin types. So many of those data sets are collected in Europe or the US, where the subjects that are sampled in those studies typically have lighter skin types. We made a real effort with MMPD to collect a broader range of skin types in our subject population. And also some of these videos contain relatively large motions, making it pretty challenging to extract the PPG signal, for example. Okay, so that's just a summary of data. So we have data sets, some publicly available, that reduces the barrier to entry for sure for academics and people that want to train these models. But what modeling techniques are the most effective? In the community started by focusing on signal separation techniques, and you can look at the work of Blazek et al. In the early 2000s to see like really impressive early demonstrations of non-contact measurement from both RGB and IR data, just looking at aggregate pixel traces across time. But those are easily corrupted by motion of the body. So subsequent algorithms leverage the fact that we can use multiple color channels to denoise essentially our estimate of PPG or respiration signals. So in this case, we're using an unsupervised learning method to extract the PPG waveform from color traces, the red, green, and blue color traces from the camera. And these red, green, and blue color traces are created by spatially aggregating pixels across each frame, and then to give a time series for a time window of video. So that's, I would say from about 2009 through 2015, 2016, a majority of the work focused on these unsupervised learning methods. And the POS methods pretty much consistently is the best performing of those algorithms. So that's work from Wenjing and his group, using physical principles to design a source recovery algorithm from spatially aggregated RGB information. And the POS method is a really nice and relatively simple to implement algorithm, and does a pretty good job for an unsupervised algorithm. However, since about 2016, focus has moved to neural methods and training supervised methods, which typically outperform unsupervised methods. However, we'll come back to the question of how that performance is within a data set versus across data sets, because of course supervised methods run the risk of overfitting, which you don't typically see with unsupervised algorithms because they're not trained in the same way. So when it comes to supervised methods, we now can go beyond just spatially aggregating the pixels from every frame of the video to create time series, to learning features from a spatial temporal input sequence. And there are, I would say, kind of three main things that have been experimented with in the input representation to these models. And all three of these are basically inductive biases that we want to leverage because we have limited data to train models. I would argue that it should, in theory, be possible to input just plain unprocessed video frames and train a model to predict most of these physiological variables directly, end to end. However, most existing work has leveraged one or more of these inductive biases. So the first is leveraging difference frames, which is essentially taking the normalized difference of each frame in a video sequence. And what this does is remove a lot of the appearance information in that frame, which is not necessarily useful for extracting the pulse signal, because the pulse signal is changing over time. We want to give the model the sort of most high density input sequence that captures that change, rather than give a lot of information about skin type, which might not be relevant. So by taking the difference of subsequent frames, what we're doing is removing things like skin type or lighting conditions from the input representation and just giving the model the change in pixel from frame to frame in the spatial input. Another thing that has been leveraged is downsampling of videos. So as I mentioned, in the unsupervised methods, we typically spatially aggregate those frames to give a single value from the red, green, and blue channels across for each frame in a video sequence. And downsampling is still very helpful for neural methods that are taking input video sequences. So in this case, we might want to take a video that's recorded in HD and downsample it quite aggressively to create input sequences that are 30 by 30 pixels or 100 by 100 pixels. And what this does is, again, remove high frequency spatial information that's not necessarily very useful for the PPG or respiration extraction, because we want to capture those changes across time and not necessarily someone's skin texture or their hair texture, which is just adding noise to our input, which the algorithm in theory shouldn't need. There are also a lot of exploration has focused on transformations of these signals. So there's been a lot of success leveraging things like spatial temporal maps, which collapse the video frame into a different representation, but still preserve some spatial and temporal information. So you can see here that different segments of the video have been extracted, different regions have been extracted by leveraging face tracking and segmentation. And then those pixels have been essentially flattened to create input spatial temporal maps. So the y-axis might be spatial information, the x-axis might be time. But there are different ways to create these input maps, which might be potentially better or more easy for a neural model to operate upon. In all cases, I would argue that these operations, these pre-processing steps, are inductive biases that help models learn. But again, I don't think they should be necessary. And I think once we have large enough data sets, we can leverage the fact that models can learn these types of things end to end. For example, if difference frames are useful for the model should learn, if we give it an input sequence of frames, to take the difference of those frames instead of looking at each frame independently. So this is an example of one neural architecture that is used to recover the pulse or respiration signal from a video using difference frames. In this case, we also input the appearance, the unmodified appearance frame of the subject in order for the model to be able to leverage some context about where the skin is in the video, because the difference frames, as you can see in the top row, you lose information about skin color, which might be useful for guiding attention, like which part of the frame to focus on if you're extracting the PPG signal, for example. This model is in purely 2D, so 2D convolutions, and then a fully connected layer, and it's predicting essentially the change in blood volume pulse for each pair of input frames. And so that's not leveraging a lot of temporal information. Subsequent work has leveraged the fact that, of course, we're learning a temporal signal here, so having a model that can learn features that across time as well as space is useful. And 3D convolutions typically outperform 2D convolutions. And a natural other thing to try, as in this work, was an RNN applied to the output of 2D convolutions to capture that temporal information. Generally speaking, 3D CNNs seem to outperform an RNN plus 2D convolutions, but 3D CNNs are pretty computationally expensive. So that's one of the things that we have to sort of bear in mind when we're thinking about how these models might be deployed. Another thing to note, as in this example and the previous example here, is that these models are pretty shallow from a deep learning perspective. So you might be familiar with models trained for other computer vision tasks on ImageNet, where there are a vast number of layers. The input dimensionality might be quite a lot larger. In both of these cases, the input, the size of the input frames is smaller because these frames are often downsampled, and the network depth is a lot shallower, partly because we don't need a lot of high frequency spatial information for this task. Again, we're trying to capture something that is globally changing across the skin or the body within the video, and we're generally making the assumption that that face or that body is pretty large in the input video. This might change, the need for deeper networks might change if there's a lot of other things going on in the input video sequence. But that would cause other problems for the learning algorithm too. The previous two examples that I gave were more traditional supervised models, but there have been a number of creative examples leveraging adversarial learning and unsupervised learning in this domain. I won't have time to go through them all, but just to highlight one example here, using GANs to train a model. So you're training a model that is producing an estimate of the PPG, but also discriminating between false and true PPG signals. And this has yielded good results, but there are also several other papers looking at other forms of self-supervised and unsupervised learning that I'll note have also had pretty effective results. And in those cases, some have leveraged contrastive learning, others have leveraged more predictive coding types of approaches, and then in this case, GANs. One thing to note is that there are some approximations we can make in the model to reduce the overall computation while still preserving some of the spatial temporal information that the model can leverage from the input sequence. So as I mentioned, 3D convolutions are often prohibitive for many applications. So even with current optimized hardware, if you have an algorithm that is that involves 3D convolutions, deploying that on a cell phone is still going to be pretty prohibitive in terms of computational load and battery life and things like that. So in this work, we we're investigating to see whether we could use 2D convolutions, but shift shift features across time using temporal shift modules to see if the model could still leverage some temporal information and get results close to what a 3D convolutional model can achieve. And this is quite an effective approach for getting a good balance between computational overhead and accuracy. So I'm jumping a little bit here between different types of learning algorithms and network architectures. So for example, this approach here could be used in the context of an adversarial training, or the model architecture here could be used in a more traditional supervised way, but just trying to give a flavor of the different types of techniques that have been investigated so far. I'll present just a slide here. There's a lot of numbers, but just to highlight that in cross dataset testing, still we've found that some of the simpler neural models tend to still be better. And the hypothesis there is that with more complex models, with more parameters, and both parameters and hyperparameters, and small data sets, we still run the risk of overfitting in this domain. So that it's not unusual sometimes for a 2D convolutional model to still give the best results in cross dataset experimentation, because that model is perhaps at less risk of overfitting to the training data set. So you can note here, DeepFizz, which is just a 2D convolutional model, achieves the overall pretty decent results on some of the data sets. Not necessarily the best across all data sets, but competitive results even to transformer models and other more complex algorithms. So I think there's a need here to both collect larger data sets so that we can leverage some of these more computationally expensive and kind of larger models, as well as just being careful about how we conclude the results when we still have limited data sets to train and test on. One other thing I want to note here is that in the last row, that is a transformer model, and many people might be asking the question, you know, that's probably the de facto standard for most vision architectures right now, and the RPPG and remote physiological community has been moving in that direction, but I would still say that results are fairly comparable between convolutional models and transformers at this stage. Again, perhaps partly due to the fact that training data sets are still relatively small. So now I want to move on from sort of high-level model architecture stuff to training these models. And first is to highlight that the number of subjects in the data set really matters. So it's not just about the number of samples, but the diversity of the appearance, both in terms of the subject's appearance due to their demographic characteristics, but also their appearance due to the environmental conditions. So you take a video of the same person under different lighting conditions, they can look visually quite different. And so we want to be able to, we want to have as much diversity in both of those parameters as we can. In these plots, you can see on the x-axis the number of unique appearances of subjects in the data set, and on the y-axis the performance of the algorithm. And in both cases, higher is better on the y-axis. And we did this experiment by leveraging the synthetic data, partly because we didn't have any data sets with 1,000 subjects in the RPPG domain that we could test on. So it's yeah, that we have to take these results with a grain of salt, because they're tested, you know, they're trained on synthetic data, and that may have some caveats to it. But eventually, once we have real data sets of this size, I'm pretty sure we'll see the same relationship. So in terms of supervised training, we've seen examples of how we might transform the input and train a model to predict either a waveform or an average heart rate or average respiration rate signal. But how can we leverage self-supervised learning? There are many videos that we could collect where we don't have paired ground truth information. And those could be crowdsourced, they could be collected through medical systems where, that they're retrospective data sets where videos were recorded, but no PPG or respiration was recorded at the same time. And so I think there's a lot of opportunity here for self-supervised learning. One of the reasons for that is in a video of a person who is alive, we can pretty reliably say that there must be a PPG or respiration signal present, because unless they're holding their breath, which is pretty rare, or they have no pulse signal because they've just had a heart attack, which again, hopefully is pretty rare, that is a sort of fairly reliable assumption. And so, and this type of assumption is not something that we can make in many other computer vision tasks. So I can't take a random image of a person from the internet and say that they're wearing a hat, right? Like that, if I was training a hat detector, that wouldn't work. But for PPG and respiration, if I have a video of a person, I can pretty reliably say that that person has a pulse signal and is breathing. And so this is a direction we've been focusing on a lot recently, and I know another number of other research groups have too. Just to give an example, to contrast existing self-supervised methods that use contrastive learning in the spatial domain to our task, there are some notable differences. So on the left-hand side, you see conventional feature similarity and how it's computed for in contrastive learning in things like in algorithms like SimClear. So in this case, we have a video sequence. Those are the anchor features, right? So that's a sequence of video frames which contain periodic information. So we're focusing on the task where we're training a model to detect some signal that is periodic. And in traditional contrastive learning, the types of transformations we would do, for example, cropping a video, right? That won't change the underlying frequency information. So if you have a video of me and my heart rate is 60 beats per minute, and then you crop that video with a different bounding box, my heart rate is still going to be 60 beats per minute. But we know that if you resample that video, so if you downsample it or upsample it, then the apparent heart rate of the person or breathing rate of the person in that video will be different. And that's something that we can leverage to create contrastive learning algorithms that learn to focus on feature representations that preserve frequency information and not just spatial information. So what you can see on the right-hand side is a periodic feature similarity, where if we shift that video across time by small time windows, so say we take a video of me from second 1 to 5, and then we move that window to seconds 2 to 6, we can make the assumption that the heart rate of that subject is still the same. So we can shift in the time domain and not affect the ground truth label. We can reverse that video in the time domain, so we can play it backwards. Again, the heart rate should be the same, right? Because we haven't changed the frequency. But we can resample that video, and we know by what factor we have changed the ground truth frequency label. So if I downsample it again, like as I mentioned at the beginning, by removing every other frame, we know that we've doubled the heart rate. We might not know the heart rate of that subject, but we know that we've doubled it. And we also know that if we just randomly shuffle those frames in that video, we're gonna destroy the periodic information. So we can use these properties to create both periodicity variant and periodicity invariant transformations, where we can increase or decrease the frequency of the target signal, and we can also create spatially altered or color space altered sequences that have the same frequency. And this allows us to frame this as a contrastive learning task, forcing the model to embed samples with the same frequency information in the same space and samples with different frequency information in different spaces in the latent representation. And these t-SNE plots show how effective that can be. So this is a t-SNE plot. This is an embedding of videos in the which are colored by the frequency of the ground truth label. So we've embedded these videos using a convolutional network, and then we've taken the learned representations of each video and plotted them and colored them by the frequency of the ground truth. And in a supervised model, it learns frequency information well, as we'd expect, because it's had training samples with different frequencies. But typical self-supervised learning techniques like SimClear don't do well. So you can see the frequency information is very scattered, jumbled. There's not a lot of structure there. And that's because the contrastive learning, the assumptions made in forming positive and negative pairs in SimClear are not optimized for learning temporal and periodic signals. Some self-supervised models like CVRL here do better, but there are ways we can improve on those even further by creating these periodicity variant augmentations, as I mentioned, by resampling videos and then forcing those resampled videos to be in different parts of the latent space than the original video. And so here's just some results showing the performance. So y-axis is error in heart rate measurement, and the different models are represented by different learning methods, I should say, are represented by different colors. And you can see that by leveraging the periodicity variant augmentations, we get the best results. And these performance improvements are maintained even when we fine-tune these self-supervised models in a supervised fine-tuning downstream step. We found that self-supervised learning in this way can also make models that are more robust to biases in the distributions of the training data. So, for example, if we had a video data set where we had the y-axis here would be frequency, and we were missing a bunch of samples in a particular frequency range. And in RPPG, this is often the case. We might have less or fewer videos of higher heart rates than lower heart rates, because it's easier to collect videos of people who are resting than it is during exercise or post-exercise. And so this is often the case. The label distribution is often sort of biased to something that's close to the mean of resting heart rates of individuals and excluding higher or sometimes lower heart rates. And so having a model that can learn to extrapolate in the frequency domain relatively robustly is helpful. And we found that self-supervised learning, where we're creating these periodicity specific augmentations, is one way to get better results, or models that are better able to extrapolate. As I've shown some results, in the tables earlier, comparing the self-supervised methods and the supervised methods, but just to kind of round out, here's a probably easier to digest representation of different models, just a few selected models, and over time, these papers were published sort of 1 to 2 years apart across time, from earliest to latest, earliest in dark red to latest in light red. And you can see we've got pretty systematic improvements across time. I would say we have models now that are sort of approaching practical use cases. Obviously, these results are these results are from test sets that are still pretty heavily curated. Our public data sets, as mentioned, are limited in diversity in terms of people's resting heart rate, in terms of their appearance, in terms of the lighting conditions and things like that. So we have to take this with a grain of salt. It's not something that, these are not results that we could say would be applicable to a real, to diverse real world conditions. But I think at least for our PPG, we're getting close to that, and that's exciting to start to think about taking this technology outside the lab. And I know there's a number of startups and companies starting to do that. Same is true for respiration and other signals. Again, I won't have time to go through all of the signals in this talk, but certainly for respiration and breathing, we've seen systematic improvements. One thing I do want to comment on is optimization of these algorithms. So all of the algorithms I've presented and results I've presented have been focused on extracting essentially the dominant frequency of that underlying signal in the time window. So we're trying to extract the average heart rate for a 20-second video sequence, for example, or the average breathing rate. So that's just the dominant frequency. But for many tasks in the health domain, getting the morphology of the PPG signal is just as important as getting the frequency. So for example, if you're trying to detect arrhythmia, it's not okay just to get the dominant frequency of that signal, because you need to know if the waveform morphology has properties that you can use to predict whether there's an arrhythmia present. Same is true for blood pressure estimation. Dominant heart rate doesn't tell you a lot about someone's blood pressure, but there is literature that suggests that morphological features from the signal can be used to get better, maybe not very accurate, but better estimates of blood pressure. And so designing algorithms that allow us to optimize for getting waveform morphology is still, I think, a very relevant and somewhat underexplored area of research in this domain. So in this case, what we might want to do is to add first and second derivative penalties to the model. So rather than just focus on the model producing the dominant, an estimate of the dominant frequency of the signal within that video, we might want to make sure that it produces first and second derivatives of that waveform accurately. And in the PPG domain, first and second derivatives are used for estimating things like blood pressure. But I would say this could also be true for things like breathing. If you're trying to assess someone's respiration pattern, knowing the dominant frequency of their breathing is useful, but also knowing the morphology of that, like, are they breathing in sharply and then exhaling slowly, or is there a different dynamic going on there? So I think it'd be nice to see more exploration of how we can get some of these more subtle waveform properties learned by these models, because one thing you'll often see, or at least in our experience you'll see, is that if you train a neural model to predict heart rate, it'll produce a fairly sinusoidal estimation of the signal, because that's kind of closer to the average waveform, and because it's not been optimized to capture the higher frequency components of that signal. Just to round out before I take any questions and then pass over to the other presenters, that some of the assets that I presented are available and then we have our workshop tomorrow. So if you're still around tomorrow, there's a workshop on computer vision for physiological measurement, where there's a number of really interesting papers on both PPG estimation, blood pressure estimation from RGB and video-based inputs. So do take advantage of these resources, and there are a number of other data sets, of course, that I showed earlier, and also toolboxes that are available that I didn't have time to present. But I think the community is moving in a really positive direction to having more reproducible code, more data sets to benchmark on, and these types of things. So I'm excited about the future in this space. Thanks for your attention, and be happy to take any questions before we switch over to Wenjing and Shuju. Yeah.
Do you have any idea of how those methods are robust compared to, with respect to the camera changes, or maybe the ISP, auto exposure, this kind of thing?
Yeah. As I mentioned at the beginning, that I didn't have time to cover many of those kind of more hardware-related parameters. These models are definitely affected by things like the bit depth of the images collected, the frame rate, the resolution, and just the quality of the image sensor, right? So if you have a very high quality image sensor with a low or high signal to noise ratio, then there's less. You can get a very good PPG signal just from looking at the green channel from a high quality camera if the subject isn't moving, for example. There are a number of papers that explore kind of systematically, like ablation tests of varying those different hardware parameters, like the quality of the image sensor, the frame rate, spatial resolution, those types of things. And the relationships are more or less what you'd expect. So if you reduce the frame rate, performance will get worse, but not that dramatically if you're predicting just heart rate. Same for spatial resolution. It will get worse generally with lower resolution, but because we often spatially average these frames before putting them into a model, it's not extremely damaging. Video compression is perhaps the worst offender here. So if a video is compressed, sometimes the subtle pixel changes that we rely on are removed by the compression algorithm, and that's difficult to recover because you've essentially you've left in the stuff that's not useful and you've taken out the stuff that is useful.
And what about auto exposure? Is it something that affects a lot?
Yeah, you'll find that most people switch off auto exposure, white balance, and these things during data collection because they cause dramatic shifts in the color space in the middle of a video, which is, even if you can filter out low frequency changes in the signal, there'll still be artifacts that remain because these are like step functions in terms of the appearance of the illumination in the scene. Yep.
What should be the distance between the camera and the subject?
That's going to be dependent on the type of imager you have and lighting conditions, of course, but people have shown that you can measure up to 50 meters with a camera with a telephoto lens, so that the signal is still present, but it will be, of course, a lot weaker in that scenario than when you're half a meter away from the camera. But most of the data sets are between about half a meter to 1 meter from the subject.
And how many pixels do you need for the face? 30 by 30, I heard you say?
Yeah, I mean, there are that's in the input to the model. People have shown, even with 9 by 9 pixels, like a very aggressively downsampled input frame, you can still get the PPG signal. But that's, of course, assuming that in your original video, like it was present, right? So downsampling doesn't harm the signal generally that much. But if I was to record a video of you from here, right, your face might be 9 by 9 pixels, but that's very different from me taking a video of you up close and then downsampling that video to like, right? So downsampling is just aggregating. But if the signal was weak to start with, then it's still going to be weak after downsampling, right? So it's not, again, it depends on the distance as well as the imager, the lens of the camera, and these things. Yeah. But I would say arm's length is sort of like a pretty reasonable thing, but across a room, it would be difficult. Yeah.
Thank you very much for that. It's very interesting to review and refreshing idea using contrasted learning. Is there a route you see for adapting to the frequency, communication style, contrasted learning to be non-contrasted? There's some works that suggesting that non-contrasted methods can be a bit more sample efficient. I don't know if there's any.
Interesting. So definitely there's differences between contrastive and non-contrastive methods. Contrastive methods, often you face the challenge of having to create, creating batches is difficult because you're creating all these negative samples, and you can often run into limitations in memory when training, especially in video tasks. So that's predictive coding types of setups, or masked auto encoding, that type of thing, are often like easier to use practically. I would say there's been less exploration in this space with those methods, but I don't really doubt they would be effective. I think they would. I think it's just contrastive learning has been sort of a popular choice. Yeah.
Something like bring your own ratings that are still self-supervised, but they don't necessarily rely on the hard negative examples.
Okay, but in that case, are you sort of masking out some of the input and asking the model to reconstruct it, or are you like?
Some destination involved. They can be quite hard to analyze and
to
understand how they work, but
yeah,
in vision they work quite well. I mean, I mentioned this because Simper particularly generalizes to this notion of soft negatives that are graded.
Yeah. So I think one thing we found with Simper is it works in a self-supervised sense, but just simply the augmentations are useful even in a supervised sense. So I think it would be also true in other self-supervised methods that if you do these augmentations, you can create more samples, which where you have a pseudo label, right? Because you know how much to up or down sample the label. Yeah.
Would you please comment on the synchronization of labels to video? To what extent do you need to be able to synchronize the ground truth to the video that you'll be able to use it on an hour basis, a minute basis, a second basis?
Yeah, it depends on what your loss function is penalizing for. So if there's work using essentially Pearson correlation between the heart rate estimate from a video sequence and the heart rate estimate from the ground truth. And in that case, synchronization is not as critical because you're penalizing the model for predicting the average frequency well or not. In most of the methods that I've trained, we use the waveform as the target. So there you need very precise synchronization, because if you're predicting like whether the PPG signal is going up or down in those few frames of the video, if it's not synchronized, the model has nothing to learn from. And what's particularly damaging, of course, is if that synchronization is different for each video across the training set. Like if there's a fixed offset, it's okay, right? Because the model can learn that. But if every video has a slightly different offset, that would basically destroy training. And we found that that's the case with several data sets where the synchronization was poor. Basically, we can't train with those if we're using a waveform level loss. that's for PPG. For respiration, of course, it's more forgiving because that's a slower time varying signal. And then for things like blood pressure, again, like blood pressure can change rapidly across time, but it's not, with blood pressure, we're often not training to predict the periodic, the sort of arterial line of the blood pressure. We're just trying to predict the systolic or diastolic value, which isn't perhaps changing on the second level, but could change from minute to minute. Similarly for oxygen saturation, unless someone is actually like desaturating at that point, you can generally reliably assume that their saturation at like frame n or n plus 30 is probably going to be the same. So it depends, it depends on the subjects, the dynamics of the underlying signal as to what level of synchronization is needed.
But in respect to the data sets that you're collecting, is there a trick that you like to use, like simultaneous triggering into your video?
Yeah. Oh, yes, that's always the best. I mean, yeah. If you can trigger the ground truth and the video at the same time, like that's definitely preferable. Like, yeah. And it's data collection is labor and time intensive. Like, it's worth doing that, I would say, in almost every case. Yeah.
Right. So not ballpark time.
No. We've had If you just assume that this device and this device have the same clock and record, like that can definitely lead to problems if you're not careful. Yeah.
So regarding the problem of if you have a subject who's otherwise alive, so there should be a signal present, but there could be some reasons why the signal might not be present. The person just very old, very heavy makeup. Like, what are some of the methods in terms of not just measuring the PPG signal, but understanding the uncertainty and the potential error in what the model has measured? Because you can imagine in many practical environments, especially if you're like incorporating this as part of some decision-making process, knowing how uncertain the input is at this point to know how much you should rely on that number.
Yeah. I think there's a lot of, just from like more conventional, so when we think about PPG, more conventional PPG like measurement devices, we have different signal to noise ratio measures, or so I think those are still probably the best, right? So if I've got an output predicted waveform, I can use statistical properties of that waveform to assess whether it looks like a PPG signal or not. I still think that's probably the most reliable route, because there's a lot of previous literature sort of doing that on contact PPG, not non-contact. Models predicting the quality, like giving you a confidence score. I mean, there are models that can do that type of thing, right? Like if you add a penalty that also predicts confidence, and you know, for instance, in your ground truth, how much noise there is and things like that. But I think we should leverage as much as we can from the contact measurement work in the domain that we're operating in, because we have data scarce. We're pretty data scarce in the video domain, so I think it's just wise to sort of leverage as much as we can from existing literature. Does that make sense? Okay. Thanks everyone for attending. I should pass over to the other presenters. As I mentioned at the beginning, the next two presentations.
Yeah, Daniel, I think you. Hey, Daniel, I think you still have a online question.
Okay, yeah, I'll stop sharing, but please go ahead with the question.
Hi, thanks for your presentation. I have a question about the backgrounds, and the background, I guess it kind of static. So I'm curious about the dynamic case. For example, while I'm walking, the environment and me are changing over time. Does it possible to monitor the vital signs in such dynamic case?
Sorry, I'll repeat the question because I unplugged the computer during that while you were speaking, and I'm not sure everyone could hear. So the question was, in dynamic lighting conditions, for example, if someone's walking or driving and you're measuring the signal, like how robust might be the algorithms be to that scenario. And I would say that's probably the most challenging context, and most methods will break down pretty quickly if there's dynamic illumination. And so I would say it's unsolved problem. Definitely for practical applications, I think you'd want to try to constrain the amount of lighting variation or motion of the subject. But there are, I think, again, like promising opportunities for neural models to learn motion robust features if we had enough data, but most data sets are pretty static, both in terms of illumination and also in head motion as well.
I see. And I also have another question, because I'm not sure the training data, if the face is kind of clean. For example, if I have some tattoos or some specific symbols on my face, does it be like, can it robust to be extract the vital signs as well as the clean face?
I don't think there's any evidence necessarily to suggest that would interfere with the PPG signal by default, but in a supervised method, for example, the model might get confused because the appearance of those pixels doesn't look like unpigmented or like untattooed skin, right? So again, this is all about bias in your training set, right? If your training set doesn't include anyone with tattoos, the trained model may well struggle in the context of analyzing skin with tattoos, because the pixels that are tattooed may not look like skin pixels to that model that's biased, right? But if you have representation in your training set of tattoos, I don't see any reason why it would.
Yes, since I'm curious about if someone design a backdoor trigger about a tattoo or some specific symbol to attack the model.
Yeah. I'm not aware of any specific work specifically doing that, but yeah.
Yes, thank you.
Yeah. Okay.
Thanks.
Hi, Daniel. May I ask a question?
Sure. Yeah, I can take one more. I think then after that, I should stop and let the next speaker go.
Yeah, sure. So I read your work about the synthetic data set. So I'm wondering, so with the synthetic data set, do you think there's still any gaps between synthetic data versus the real collected data regarding the synthetic data quality? Can we say directly go to synthetic data to train the model? Yeah, so I basically want to know, say, what's your opinion on using synthetic data versus the real data? Yeah.
Yeah, I still think it's too easy. The synthetic data is too simple because we can't model all the complexity of the real world in terms of both like the imager noise as well as the environmental and illumination noise. So that if you like with SCAMPS, that's one thing we found pretty quickly, is it's useful for training, but it learns a pretty simplified representation. So if you apply it to real videos, it can do a decent job, but it'll still it'll fit pretty fast to that. If you train a model just on synthetic data, you'll see the loss curve drop pretty quickly because the model can very quickly learn the mapping between pixel changes and the PPG. And so I think, and this is true also with like generative AI types of augmentation, like motion augmentation. We see similar types of properties because we're often only changing like one aspect of the video and not like if you do motion augmentation of a subject in a video, it might not perfectly simulate how the illumination of the face changes, right? There's going to be artifacts in those videos, and the model can use a shortcut to get good training performance, which doesn't generalize the test performance. But I still think it's a promising direction. Like I still think synthetic data will play a pretty important role, partly because in healthcare, data is so privacy sensitive that we need ways to like just exploit as much as like data creation in as many ways as we can.
Okay, thank you.
Yeah, okay. I will start sharing my screen. Can you see my screen? Check. Yeah, can you see my screen? If you can see my screen, I will start. Okay, I guess it's okay to see the screen. Okay. Yeah, yes, great. Yes. Okay, so I will start the second part following Daniel. So my part will be the camera-based physiological measurement and its clinical trials in China. I'm Wenjin Wang from the Southern University of Science and Technology. Yeah. So as you can see that for this tutorial, we're talking about the contactless health monitoring. We can use the camera as a contactless sensor for measuring various vital signs like heart rate, respiration rate, SpO2, blood pressure. And now my part is more focused on its applications in real life, and particularly focus on the clinical trials and studies. And from this, wait, let me change my. From this image, you can see that we now apply the cameras in various clinical units like the NICU, NICU, ICU, HDU, high dependency unit, and also for the surgery recovery assessment. We also put the camera into the sleep centers for sleep staging, for hand hygiene monitoring, and combining with the stethoscope, the microphones for the remote telemedicine. And yeah, so we consider that the camera-based monitoring will be a very valuable new stream for the patient care. For example, in the neonatal care units and for the intensive care units. So my part actually has two different chapters. The first chapter is the camera-based vital signs monitoring, but since Daniel already gave an in-depth overview on its techniques and models, I will be more focused on the clinical studies. So first is a very brief introduction from the PPG to the camera PPG. As we can see that the PPG is the abbreviation of the photoplethysmography, and it's not a new technique. It has been used in various scenarios like the finger oximeter, for example, the fitness band, smartwatch, they all use the PPG. But as you can see that there's a significant difference between the contact PPG and the camera PPG. For the contact PPG, that we have the light source and the photo detector that are attaching to the human skin, because we can have a very specific position or distance between these two devices. We can construct a banana-shaped optical path beneath the skin. So that means we can measure pretty strong PPG signals, because if the signal cannot penetrate deep into the skin, it cannot be reflected and received by the photo detector. But now if we move the light source and the photo detector, for example, here is the camera, we move these two devices away from the skin. Now we're actually measuring a combination of the different reflections from the skin surface, like the light deeper from the skin tissues, and also the light from the shallow layers of the skin, and even the specular reflections that does not penetrate into the skin. So the total amount of the pulsatile component in the optical signal becomes weaker. And that means it's more difficult to extract PPG signals from the optical signals. And so the core algorithms we established in this field is actually how to extract the pulsatile component or pulsatile signals from the camera signals. For example, giving a video, as you can see, giving a video, there's a living subject, and we can measure optical signals from its living skin. But you can see that the signals, the optical signals, is a combination of different sources. For example, the pulse, respiration, body motion, lighting changes, sensor noise. And we want to extract the pulse. And that means we want to suppress distortions. But also, we want to separate a PPG component and a non-PPG component. And that's called the source demixing. And in this field, we have different methods to do the source demixing. For example, as Daniel already introduced, we have the blind source separation and the deep learning-based modeling, and also the knowledge-based modeling. And this part is kind of the focus of our group. And you can treat this equation as a very, very basic process to demix the sources. Like the C is the measurement, the color signals we measured, and the source are the PPG and the non-PPG components. And the W is the demixing coefficient. And this demixing coefficient can be derived by unsupervised methods like a PC, IC, can also be derived by deep learning, supervised learning. And we will share how it can be derived by knowledge modeling. And I will introduce 3 types of the modeling using the optical physiological principles. And then the first one is the PPG knowledge-based modeling. And then you can see that this is an example of the signal that we measured from the living skin of the subject. And you can observe that there's a very specific pattern between of the PPG amplitude between the 3 channels. We can see that the green component, of course, in this signal is after DC normalization. You can see that the green channel has the highest amplitude, then second by the blue channel, and the red channel has the minimum PPG component. And we did this experiment on a large scale of the subjects, including different skin types and also the skins illuminated by different light sources. And we can see that they follow such a pulsatile distribution in 3 channels, that the green channel has the maximum pulsatility, then the blue channel, then the red channel. Why we can see this phenomenon? And we consider that it's actually a combination of the 2 facts. The first one is that the light have the different wavelength according to the light source we're using. So you can see that the red light has the deeper penetration depth into the skin. For example, the 2 millimeter to 3 millimeter, and the green has the shallower penetration depth into the skin, like 0.5 millimeter. And the blue channel, the blue light actually cannot penetrate very deep into the skin. So regarding the penetration depth of the light, it's actually following this order, which is the red, and green, and blue. But if you see the absorption sensitivity of the hemoglobin, it's actually the opposite. The blue channel has the highest absorption, then the green channel and the red channel has the minimum absorption. And if we combine these 2 different effects, then we can get this very specific or very characteristic ordering of the channels in terms of the pulsatility, which is the green, blue, and red. So that means that if we extract different spectral components from this setup, like the blood absorption spectrum, skin lining spectrum, camera filter response, and lighting spectrum, and we integrate all these spectrums, that means we multiply this spectrum, then we can get a signature. And this signature actually representing the ratio of the PPG component in 3 channels, the relative ratio of the PPG string in 3 channels, which is, for example, the 0.3, 0.7, 0.5. And if we know this signature, then extraction becomes very simple. We can do a least squares projection, which is a one-step projection, because the least square projection has a closed form solution if we know its regression vector. So if we have a single signature, we just do a one-line MATLAB code. It's actually one-line, one-step extraction. And just using this PPG signature, we can extract the least square signal using this signature by projecting the 3-channel color signals onto this direction. But this is not very robust, because if we move the setup to a different lighting condition, or the setup is polluted, then the signal is not representative for the current situation. So we can also keep the knowledge a bit more relaxed or more flexible. So we can define multiple signatures and extract multiple least square signals, and then use a quality metric, for example, SNR, to do the selection. And this algorithm has been used in the single element remote PPG. So for the single element, as you can see in this video, because for the sleep monitoring, it's a very private scenario. So for the single element, that means we combine all the pixels, all the spatial pixels into a single pixel and extract the pulse signal from a single pixel. So the skin pixel and the non-skin pixel are highly mixed. So that means that the knowledge, the signature is not robust. And then we can use the multiple signature method to still acquire, to obtain a relatively clean pulse signal. And all these details can be found in the paper. And for the second model is the distortion knowledge-based model. So the first model is that if we know the signature of the PPG, we can do the least square projection to extract this signal. But the other way of thinking is that if we know how to model the distortion component, then we can estimate the distortions like the intensity signals, specular signals, and then remove these signals from the 3-channel signals, and the remaining one will be the pulse signal. And this is from our model, which we call the dichromatic skin reflection model, that we model the optical signal is actually a linear combination of the specular reflection and diffuse reflection. And specular reflection means the direct mirror-like reflection from the skin surface. These are actually the distortions, the noise. And we can only extract PPG component from the diffuse reflection. So from our group, we derived 2 methods. The one is the crawl method derived by Gilda Hen. And also the other method from our group is the pulse method. Actually, the essence of these 2 methods is that we find a projection subspace, and this projection subspace is an orthogonal subspace that if we project an image or project the signals onto this orthogonal subspace, we can separate specular component, intensity components, and the positive components, because the specular variation is actually caused by the motions and also maybe the lighting changes, and the intensity variation can be caused by the distance change between the subject and the light source. And the third direction orthogonal to these 2 directions is relatively independent to these 2 types of distortions. So this is the rationale, or say the essence of this approach, that we have the 3 channels of the signals. These are our measurement. We find 2 subspaces, the chrome or pulse, and then we first do the first projection, is projection 3 channel signals onto the plane that orthogonal to the specular direction or orthogonal to the intensity direction, because we want to first eliminate this distortion. And then on this projection plane, the orthogonal plane, we find the other direction, which is orthogonal to another type of the distortion, either the specular or the intensity variation, and then remove this distortion on the plane. So that means we measured two types of the distortions, and the third signal is orthogonal to that. And this method only requires 3 lines of MATLAB code, and it's generally applicable. For the third method, and we propose, is the PPG plus the distortion knowledge modeling, that we model both the PPG signals and the distortion signals. Why we have to do this? Because as just the audience asked, can we measure the PPG or the heart rate in extremely challenging case, like when a person is walking or running? Actually, we did such experiments and also study that we try to measure the PPG, the heart rate, from the person who is running on a treadmill. And in this case, it's very challenging because the motions are much more significant than PPG component. And second, because it's a running exercise, these type of the motion are also periodic. So as you can see from this spectrogram, this is the pulse signal in the middle. And these are the vertical motion signals and the horizontal motion signals. And it's very difficult to separate motion from the pulse. It's stronger and it's also periodic. So how to solve this problem? We propose the method to eliminate the distortions more explicitly. And we are kind of inspired by the smartwatch, because for the smartwatch, it uses the optical signal, which is the green channel measurement. It also has the motion sensor that measures the motion. And actually, then we think that we can exploit the 2 types of the signals from the camera. For example, you can see for the subject, we can use the facial landmark tracker to track these facial landmarks, the key points. And from the key points, we can, from the patch targeting the key points, we can extract 2 types of the signals. The first signal is the optical signal, like the multi-channel color signal, like in the near infrared or in the RGB. And the second type of the signal is the motion signal. This can be generated by the X and the Y coordinate of the facial landmark. So that means we have 5-dimensional signals, 3 optical signals, and 2 motion signals. And then here we can extend our PPG signature to a discriminative signature by adding 0, 0, and then do the least square projection. This means that we want the motion as the 0 contribution or 0 weight in our final projected signal. So it's very simple. It's just measure both the optical signal and the motion signal and extend the PPG signature with the 0, 0 to tell the least discretion that we want motion as 0, has no contribution in the final output. And in this way, we can generate pretty motion robust signals. And you can see this comparison. I made this recording in the near infrared because it's usually more difficult to extract PPG signal in the near infrared because the blood absorption sensitivity is much lower. And we also applied this method in the fitness. As you can see that the subject is running on the treadmill, and this is the camera that captured the subject face and measured the PPG signal from the face, and this is the spectrum of the heart rate. So in this case, the essence of this method is that we explicitly measure the motion signal, and then we suppress this motion signal during the PPG extraction, the pulse extraction. And for this application, we also did another very interesting study in my group currently in China, is that we measured the pulse rate variability, or say the heart rate variability. It's a kind of the surrogate for the subject that just after the running exercise, because we consider the windowing, the time window after the intensive exercise is a window for scanning the heart diseases. And from the pulse rate variability, we can see lots of these like the cardiac disease, like arrhythmia, atrial fibrillation. Yeah, this kind of the programs. And in this study, we measured 12 features of for the heart rate variability analysis, including 3 categories of the feature, like the time domain feature, frequency domain feature, and the nonlinear feature. And these are very standard definitions for HRV in the contact-based measurement. And for this experiment, we collect 2 groups of the people. First group is the subject with the exercise habits, and the second group of the people are the subjects without exercise habits. And we have 2 major findings. The first one is that if we just measure the RPPG signal, which is the camera PPG signal, before and after the exercise, we find they have the better performance than the PPG signal. And this can be understood because the camera, although it's non-contact, but we can use this channel combination method to eliminate distortions. And second, that the camera is also an imaging method. We can exploit this spatial redundancy to improve the accuracy of the measurement. And the third one, I think it's also important, is that for the subject in this scenario, before an exercise, the subject is standing on the treadmill in front of the camera, which can be relatively relaxed or relatively stable, but the palm can have more degree of the freedom of the motion. And you can see that for the heart rate before the exercise, the subjects, the group of the people that has the exercise habits, the rest heart rate is generally lower. And for the heart rate after the exercise, you can see that the people who has the exercise habits, their heart rate has the faster recovery rate after the exercising than the people without the exercising habits. And we measured the 12 HRV parameters from them, and this can also show that we can differentiate these 2 groups of the people from the heart rate variability. And this has been reported in our paper. And the other measurement is the SpO2. And just to give a very brief introduction here, the SpO2 measurement is actually that the principle is very similar to the contact-based measurement, like the finger oximeter, that you have 2 different wavelengths to measure the PPG amplitude. And the principle is that if our blood is full of the oxygen, its absorption curve is this the red curve. If we hold breath and we stop breathing, then the hemoglobin absorption sensitivity becomes this blue curve. Yeah, and then if we use the 2 different wavelengths to track the PPG amplitude, we can see that the PPG string at these 2 wavelengths becomes the opposite. So that means if we track the relative PPG amplitude change, we can actually reconstruct the SpO2 signal. And so we have 2 different methods to measure that. The first method is the ratio of ratio method. It's a very standard method that has been used for the SpO2. So we have 2 wavelengths. One is the red, the other one is the near infrared. We measure their PPG signal and their strength. AC of the DC, and then take the ratio between these 2 signals. And if the SpO2 is decreasing, you can see that this ratio is changing. And then we build a very simple model. We can build a very simple regression model to map this ratio of ratio to this absolute SPO2 value by this regression line. And this is for the two wavelengths sensor. But for the camera, our benefit is that we have multiple wavelengths. So referring to the multiple signature method, we can actually define multiple different signatures to do the projection, to do the regression. And then we can select a signal that has the highest quality, because this signal can be represented by the current signature. So if we find the signal that has the best quality, then we can find its corresponding PPG signature. And this PPG signature represents the current SPO2 level. But now for this camera-based SPO2 setup, we have another question, is that which wavelength to use? Of course, the best setup is to use the red and the near infrared. The reason to use the red is that we can see that there's a strong contrast between the hemoglobin and the deoxygenated hemoglobin curve. Yeah, if the contrast is larger, that means its sensitivity to capture this SPO2 change is better. But the problem is that we cannot shine a red light on the subject face, especially in the sleep monitoring. So the better solution, the more practical solution for camera SPO2 is that we move the red channel to the near infrared channel. For example, use the 760 nanometer and the 905 nanometer. But you can see if we move from the red to near infrared, then this contrast decreased, right? This contrast decreased, and that means the sensitivity will become lower. And indeed, we proved that, like in this experiment, in this study, we construct a setup that including 4 different wavelengths. Yeah. And from these 4 wavelengths, we split into 2 different setups. One is the red plus near infrared setup. And the other one is the full near infrared setup without a red channel. And we compare with the 4 finger oximeter sensors as the reference. And from this measurement, including more than 20 subjects, you can see that the red near infrared indeed has better this regression. Yeah, because its regression is more compact than the full near infrared. But for the practical setting, especially for our use case in the hospital, we have to choose the full near infrared. Yeah, the reason is that we cannot shine a red light on the subject face. And the other question we have is that, can we do the visible light SPO2? Yeah, for example, if in some clinical scenarios or some use cases, like for the child care or the baby care in the daylight condition, we actually already have an active light source. For example, the red, we can use the red and the green. And we did this study in our lab that we compare the setup. We investigate these 2 setups. One is the full visible setup, green and the red. Compare that with the red and near infrared, these 2 options. And our finding is that it seems that it's still feasible to measure the SPO2 from the visible setup, but its performance is clearly worse. And the worst performance is shown on 2 parts. The first is that between the subjects, the variation is larger. Like if we measured the 20 subjects, the variation between the subjects is larger. And we consider that this is because that the penetration depth between the green and the red are different. So the penetration depth of the red and the near infrared are closer, yeah, because they all can go relatively deep into the skin to sense the arterial blood. But the green can only go to the arterial least, Yeah, it's the small arteries. It cannot really sense as the same depth as the red. And different subjects, like their skin types are different, like the thickness, the water, the fat, the density of the could be different. Then this can cause a variation among the subject, and that will cause a problem for the calibration of the SpO2. And second, we find that even for the same subject, as you can see for these first row and the second row, the first row is the SpO2 distribution on the forehead of the subject. Yeah, this is measured from the visible, and the second row is the distribution of the SpO2 of the red and the near infrared setup that records the simultaneously with the visible setup. And you can clearly see that even for just a single subject, its spatial variation for the SpO2 measurement is less in the near infrared. So from this study, we conclude that we would conclude that it's still feasible to do the SpO2 measurement in visible lighting condition, but its performance as compared to the near infrared is worse. And we have to be very careful on the calibration. And for the third measurement is the blood pressure. And our group derived a very interesting method to measure blood pressure. It's a new principle that we also refer to the contact-based measurement. We call it the pulse transit time-based blood pressure. We measure the PTT and then to do the blood pressure calibration. But this PTT is different from the multi-site PTT. And the multi-site PTT is actually quite a well-studied topic. That means, for example, we measure both the PPG signal from the palm of the subject and the PPG signal from the subject forehead. And then there's a delay because it takes the blood to travel from one side of the skin to another side of the skin. So we can measure the pulse transit time in between, and this has the negative correlation with the blood pressure. But if we measure the multi-site PTT, then we usually require two different skin positions, two different skin sites, and this is not easy to use in practical setup. So for our study, we study another principle, which is the different wavelength-based PTT. From this figure, you can see that the near infrared and the red light, they can go deeper into the skin to sense this hypodermis. But for the blue and the green, they can only sense pretty shallow layers like the dermis layer. And that means the red and the near infrared, they can really sense the artery blood. And this green can only sense the arterial-less blood. And that means if we use a high-speed video camera, we can see from the blue channel, from the red channel, these two PPG signals, there's a tiny phase shift. And this phase shift is caused by the time that it takes the blood to travel from the deeper skin layers to the shallow skin layers. So that means we do not, by this method, we do not need two different skin sites to do the measurement. We can just measure a single skin site, but from different skin layers. And we construct our setup. One thing need to be mentioned is that if we want to use the RGB sensors, like if we want to turn RGB sensors into a multi-spectrum RGB plus the near-infrared sensor, we have to use the narrowband optical filters. This is possible. Yeah, because there's a IR cut filter in the regular RGB cameras. We can just remove that IR cut filter and put position a narrowband filter. Then we can change a RGB camera into a near-infrared plus a visible range camera. And from this setup, using a high-speed, high frame rate, we can quite clearly see that there's a phase shift between the near-infrared channel and the green channel. And we did the experiments on 9 subjects, that before the exercise and after the exercise. Yeah, and you can see that for 9 subjects, for the rest condition, which is the blue bar, they are before the exercise, and the PTT are relatively larger, right? Because the blood pressure is lower, the PTT is larger. And if they did the exercise, the activity, and then we can clearly see that the PTT in a millisecond, all the subject has the PTT reduced. Yeah, because that means the blood pressure increased. The blood pressure increased, and the blood flows faster. So the PTT is smaller, and then we can do the regression. Use this calibration model to do the regression from the PTT to the SDP and DBP, the systolic blood pressure and the diastolic blood pressure. And again, we repeat this measurement on 17 subjects in 2 weeks BP tracking. For this measurement, we use a stronger, more intensive protocol, which is the ice water stimulation. So we ask the subject to sleep in the bed and put their hands into the ice water to increase the blood pressure in a very short time. The good point of using the ice water stimulation is that subject head can be supported by the pillow, and without the motion like the generated by the exercise. So the measurements are much more cleaner. And then you can see that for the PPG imaging, before the ice water stimulation and after the ice water stimulation, you can clearly see that there's a post-transit time change. And we replicate this, we reproduced these experiments in 2 different ways for the same subjects. And you can see that before and after the ice water stimulation, there's a significant difference in their post-transit time. And we also compare to the cuff-based measurement, which is our reference. And for these results we obtained, it's already pretty close to the CFDA clearance. The CFDA is the Chinese FDA, and now we are moving towards these the medical products. And I will introduce more into the details later. And the last one is the morphology-based blood pressure measurement. This from the morphology of the PPG signal, we can also derive some like the surrogates measurement, because the PPG waveform shape is related to the artery stiffness. Yeah, you can see for this example, for young people, its vessel is more relaxed, more flexible, and then we can see this dichrotic notch, and this reflect the wave in the diastolic phase. But for the older subject, its artery is stiffer, and then we cannot observe this dichrotic notch. And for this paper or for this study, we propose to investigate the impact of different wavelengths on the PPG morphology. Yeah, and this is, we find this is a very interesting, we have a very interesting observation that although the green channel has the best positivity, the green channel has the best SNR, but it's not the optimal channel for measuring the blood pressure related feature. Yeah, you can see here that the green channel indeed has the strong positivity, its SNR is higher. But since it cannot sense very deep skin tissues, it does not really measuring the property of the artery. So we propose to use the near-infrared channel, because for the near-infrared channel, you can see very clear this reflective wave and the dichrotic notch. And comparing the red channel can also penetrate relatively deep, but the red, as mentioned before, the red channel has the very low positivity. So its SNR is not very good. So comparing the red and the near infrared, we recommend to use the 850 nanometer in the near infrared, because for this, channel. It has the better possibility than the red, and it can still sense the pretty deep skin layers. Yeah. And then the last one is that a new technique we're currently investigating from in our group, which is the structured light-based physiological measurement, that we want to use the laser to mimic the point source of the contact PPG to measure the stronger PPG signal. And we have already proved that in the paper. So why we want to use the structured light imaging? Because as mentioned before, that there's a very good property of the contact-based measurement is that it's using the point source. If we're using the point source, and we can control the direction of the light, right? We can control the direction light, and then we can we can use the camera or photo detector to measure another side of the skin. Usually, there must be a distance between the incident light and the reflected light, because we want to guarantee that the photons has the deeper penetration depth. If we measure the photons penetrated reflected here, then that means the photons already has a long path, go through a long path into the skin. If we measure the photons reflected here, it's closer distance, right? And that means it has the shallow penetration depth. If we measure the photons very close to the incident light, that means it has the much shallower penetration depth. So if we shine a light, for example, on a baby, this is what we call record in the NICU. If we shine this a structured light on the baby, and we measure its spectra, we can clearly see that for the skin reflection and non-skin reflection, its reflection pattern is very different. For the skin reflection pattern, you can see there's a blurry circle, a blurry pattern. And this blurry pattern is caused by this multi-layer skin penetration. And for this non-skin, like the background, you cannot see such a pattern because there's no light reflected from this object, because the skin is relatively, let's say, it's a different type of the material that the photons can go deep into the skin and reflect back. Then you can see this blurry effect. And that means we can measure this laser spectrum and then use the outer circle to measure the PPG. And we can get much stronger PPG because it guarantees the penetration depth. And we have shown this on the living skin detection. It's very interesting because we see people try to use the PPG to detect living skin, but the problem of the PPG is that you require a time window to measure a PPG signal, and it's usually like 3 to 5 seconds as the minimum, and it requires subject to wait in front of camera. But if using the structured light, and we can measure how blurry the circle is, right? Like using energy gradient function we derived, it's also very simple function. And if we're measuring the energy gradient of this spectral, the laser speckle pattern, we can see that for the living skin and the non-living skin, like this doll face or the photo, actually the pattern, you can see the pattern are very different. Yeah. And just by using a single image, we can use this multi-layer skin property to differentiate whether this is a real face or it's a fake face. And this is what we have done on the anti-spoofing. The next step is towards the SpO2 blood pressure measurement, use the structured light. Okay, and so I have to speed up. So for the first part, I have introduced this the modeling, the optical physiological modeling, and also the new techniques we're currently investigating from our group. And for the second part, I will Yeah, and if you are interested in these techniques, you can refer to our book, which is edited by Xu and myself, and it will give you a more thorough introduction of these technologies. And the second part is the clinical trials and studies I organized in China. And the first clinical trial is in the ICU, intensive care units. In this scenario, you can see that we use the CCTV camera that installed in the ICU. This is the CCTV camera that we're using, and this is the patient monitor, which is our reference, and it records the subject face and chest, and we can extract the heart rate variability, respiration rate, SpO2, blood pressure from this camera. And we already get more than 80 patients data in our data set. And for our preliminary studies, we have shown the results on the heart rate and the breathing rate. And currently we are writing a paper on the heart rate variability and SpO2. So for the preliminary measurements here, because the space is quite limited, I only show 22 deteriorated ICU patients that are all longer than the 10 hours continuous monitoring. And you can see these are the ICU patients, and these are the heart rate heat map, respiration heat map. And for two different focus modes, the far focus and the near focus, we can see that it's the MAE are pretty good. They're all below the 2 beats per minute. That means it's already in the range of the FDA clearance and the CFDA clearance. And we also show that it can improve the clinical flow for the ultrasound diagnosis, because for this procedure, the clinicians, they need to detach the ECG sensors, PPG sensors from the patient body. But if we're using the camera, they do not need to take away the sensors and put them back onto the patient body again after the diagnosis. By using the camera, they just do the ultrasound, and then there's no interruption of the measurement. And for the ICU patients, we also show that the benefit of using the camera is to measuring the facial attributes. For example, of course, we'll try to use the camera to measure the physiological signals and compare that with the reference. But the camera has another advantages that the contact sensors, they do not have. For example, measuring the eyes, right? Because from the eyes, it can tell the many information, like it can label the sleep and awake percentage of the patients, like if the patient is sleeping and the patient is in the waking stage, and their sleeping time. And this can give very useful information for their recovery to the clinicians. And for this measurement, we collect 48 critically ill patients in the ICU in the Third People's Hospital of Shenzhen. And we typically measure the eyes. Yeah, from the eyes, they can tell like the sleep, awake, and also if the patient is deteriorated. And we derived two methods. One is the handcrafted feature-based method. For example, we extract the geometric features, Hawk features, color informations, like color histogram features, and feed into a SVN classifier, and to do the classification of opening and close. And the other method we derived is the deep learning-based method to do an end-to-end learning, like using the eyes and the face as the input to the network, and then to do the classification. And these are the results which will be discussed more thoroughly tomorrow in our workshop. For this measurement, we find we used, in total, we have 48 patients, and we used 9 patients among 48 patients to do the testing, then the rest to do the training. And for these patients, we can see that the Hawk plus RGB plus SVN method, conventional method, it's not worse than the deep learning based method. Yeah, that's our conclusion. And for the deep learning based methods, if we output visualize their intermediate layers, like the pudding layers, we can see that indeed that the tensions or these the weights are put on the eyes. So that means that our network indeed learned the sleep and the wake, these two different states. And we can use this as an annotator to annotate, to label the amount of the time, to calculate the amount of the time of the sleep of the ICU patients. And the second clinical trial is for the NICU, for the preterm infant monitoring in the hospital, where we collect the 60 neonates, preterm neonates. And in this setup, we collect 3 different devices, use the 3 different devices, the EEG device to capture the brain waves, because we want to do the sleep study, the brain study, the sleep staging for the preterm babies. And second is the patient monitor. We want to do the benchmark. And the third one is the camera here. You can see the camera device. And here I just show 10 infants, for example, because we don't have enough space in these slides. And this is our domestic chip. So we already integrate our algorithms to this embedded device to measure the baby. And these are the heart rate and the respiration rate. It's pretty same as the ICU. In the resting state, the heart rate and the breathing rate, we get pretty good performance. And for the moving state of the baby, yeah, because the baby is moving, they're quite irregular and quite intensive, so the measurement will become worse. Yeah, and there's a significant difference between the NICU and ICU is that for the ICU, the patient almost has no body movement. Yeah, and so usually we can get a pretty high quality results. But for the NICU, for the preterm babies, they usually have quite intensive movements and crying. The baby also crying. So the performance will be worse than the ICU. And in addition to the measurement of the heart rate, respiration rate, we also measure the heart rate variability, and it's still under the paper is still under the reviewing. The measurement of the HRV is quite important for the preterm baby because it can be used for the sepsis detection, deterioration warning, and the sleep analysis, and also to analyze their brain development, because that's related to the cardiovascular system and the neural system. And we also measured 12 standard HRV parameters from the baby in this study. And in this, in the NICU, we also did another study. This will also be reported in our tomorrow's workshop, is that we collected 200 newborns. But these are not really the videos, these are the image photos, because we want to investigate if we can measure the infant weight and height from the single image of the baby. And it's quite, it will be a useful tool for the I would say for the parents, because usually the preterm babies, they have a low weight, and the parents, they want to track their growth rate. Yeah, and if we can deploy such a model on the mobile phone of the parents, then they can do such a growth tracking. And for this study, we use the mobile network and to estimate, to do the regression of the height and the weight jointly in a multitask model. Similarly, we can also do the sleep-awake detection, the NICU. The method is pretty similar to the ICU, that we crop the eyes of the baby and use the eyes to do the classification to check if it's sleeping or it's in wake stage. Yeah, and I think this is a clear benefit as compared to the contact sensors, because if we're use the smartwatch to do the sleep and awake staging, it's usually use the motion signals. Like if the subject is not moving, then it's assumed in the sleep stage. But from the camera, we can directly to sense the eye opening, and this is a very clear facts for indicating the sleep and awake for babies. And this method can be used for the sleep time estimation, sleep staging, modeling, and infant sleep health. And in addition to the video monitoring, we also analyze the cries of the baby, because the cry can tell many information. Like for example, the first one is the cry detection and the warning. And the second one is to use the cry signal to track the respiratory system. Yeah, like the respiratory system development. And we can also investigate the reasons of the crime, like if they're hungry, they're in a big pain, or in other conditions. Yeah, and for this study, we just put a microphone next to the camera, and then for the next step, we will do the the multimodal analysis across the video and audio data. And the third study I organized is in the sleep center, like for the sleep monitoring. And this is have been done in the Netherlands on the OSA patients. That's a different group of the patient that has the respiratory problem. So we typically measured the breathing rate, heart rate, SpO2 from the OSA's patient. If they do not have the breathing, then the SpO2 will drop. So the SpO2 is a strong indicator for this setup. But after I returned back to China, our focus is more on the sleep staging. And this is the trial organized in the People's Hospital of Shenzhen. And in this setup, you can see that I construct this 64 leads PSG reference as a PSG device as the reference, and compare with the video. And we have measured 11 volunteers for the overnight sleep monitoring. And different from the OSAS patient, were not very interested in the SpO2, because SpO2 does not tell much about the sleep quality. For this measurement, we are more interested in 4 parameters: the heart rate, breathing rate, heart rate variability, and the leg motion. The reason to put more focus on the leg motion is that we find that for the PSG reference, it has many sensors, electrodes attached to the legs to sense the leg, because it considers that if the patient, if the subject has less good sleep quality, its leg motion there'll be more leg motions. And our perspective insights is that 4 conclusions that for this study, we have 4 classifications, 4 sleep state classifications: awake, REM, the rapid eye movement, the light sleep, and deep sleep. And our insights are 4 points. You can see that the respiratory signal and the heart rate signal, they can all be served as the main feature for sleep staging. For these 4 sleep stages, heart rate, breathing rate, they can clearly differentiate that. The heart rate variability cannot differentiate awake and sleep very well, but it can tell a clear difference between the REM, light, and deep sleep. And the leg motion is a powerful feature that can accurately separate sleep and wake, but it cannot tell the difference between the light sleep and deep sleep. And in addition to that, we also measure the sleep postures in the sleep scenario. But I won't go very deep into that because the limit of the time. And for the sleep monitoring, we are also investigating the privacy protection technology, like using the optical defocused camera to protect the privacy. So that means we optically defocus the camera, so you cannot identify the face of the subject. So this is kind of this is a compromise between the single element and a high resolution camera. The single element is that you only have a single pixel, but you lose too much spatial information. You cannot do the poster detection. You cannot do the in-bed or out-bed detection. But there's an intermediate stage in between, which is defocused, that you cannot recover the face of the subject, but can still do some vital signs monitoring and sleep poster detection. And the other study we did is the thoracic surgery rehabilitation. So this is in another department. In this study, we're not interested in the respiratory rate of the patient. We're more interested in their respiratory symmetry, because this is a kind of in the clinical routine that the clinician will sense the symmetry of the respiration to check if the patients recovered from the non-surgery. And here we compared the CT images with our camera respiratory images. You can see that after the recovery of the patient, the respiratory phase and the respiratory amplitude become symmetric. Speed up. And then the last study we did is the wellness stethoscope for the children's CAP. It is the children acquired pneumonia. So we did a study including the closer to 200 patients in the hospital. And this has been published under the TBME this year. So for this study, we are not using the camera, but we're using a microphone and an amplifier to obtain the body sounds, like the heart sound, the lung sound from inside of the body, because we consider that if we only measure the optical signal, it's always related to the cardiorespiratory property, but it cannot really reflect the non-disease of the inside the body. So we propose a video plus audio monitoring. In this setup, we can use a camera to still capture the basic vital signs, and the other doctor used the stethoscope, the wellness stethoscope, to measure the body sound, like the lung sound, and then for the remote prescription. And we also, for this method, for the design of the method, we used deep learning, like for example, contrastive learning, to do the recognition of the non-disease based on the microphone signals. And also we also applied the transformers to improve the recognition rate. And this method is co-developed with a very famous professor, Zhong Nanshan. And we are now working towards the 5G remote consultation, use the video plus audio, and this paper is almost accepted, has a high impact factor of. Yeah, and finally for the products, I won't go very deep into that. So we have used the camera. We integrate camera on the CT and MR machines to do the gating. For example, for the respiratory gating, to improve the scanning of the MR for the MR imaging, and also we also try to use the camera PPG imaging to do the cardiac triggering for MR. And yeah, this is the pipeline. Like we use the PPG signal as a trigger signal to trigger the scanning, and we compared, for example, the ECG trigger, PPG trigger, and the camera trigger. And now, upon my return back to China, we are now more focused on the baby monitoring and the elderly care. So we are also working on the product, like embedding our smart algorithms into these camera sensors to do the baby sleep analysis and also the elderly care. And currently, as you can see, that I'm organizing this multi-center clinic trial at 6 hospitals in China. Most of them are in the Canton and also in Beijing. And we also compare the different products. And now we are moving towards the FDA and the Chinese FDA clearance to make these technologies as a medical products. Yeah, so finally, thank you. And if you have any questions, I'm happy to answer that. And you can also contact me by email or contact me by WeChat. Thank you. So if you have any questions, I'm happy to answer.
Hello, Wenjie. Yeah, thank you for the excellent talk. So I have a question regarding the post-transition time-based blood pressure. So I'm wondering whether you have studied the height of the person, whether that can affect the post-transition time. Say, if the person's height is very tall, and then the transition time may be longer than a person which is very short. So I'm curious about this point. Or yeah.
That's a good point. So we indeed studied the transition time. For example, for this study, for the GPHI paper that we published, we indeed studied that. So it's a fundamental problem. Like if we want to use the camera PPG to capture the PPG signal and use that as a surrogate of the ECG to do the cardiac triggering, you can see there's a pulse arrival time or pulse transit time delay. And this delay is actually related to the height of the person. And this has been reported in this paper. If the person has the height is like it has a long neck or has the height is clearly it's taller than others, you can see the transit time is longer. Yeah, and we already reported this correlation between the PTT and the pulse transit time. So the person's height need to be considered in the calibration. If we are using the multi-site PTT, for example, if we are measuring the PTT from the finger to the head, or from the ECG to the head, from the PTT between the ECG and the PPG at the forehead, we must consider the path of this pulse traveling path. But for this study, for this PTT is a very different principle, because we're not measuring the PPG signal at two different skin sites. We are measuring the PPG at a single skin site, but from different skin layers. Yeah, so the height issue, I think the height issue will not be translated into this setup. Yeah, but the skin thickness can be another issue. Yeah, but our assumption is that the variation of the skin thickness as compared to the variation of the body length, it's much smaller, in a much smaller range. And it's also reported in our two papers. One is on the exercise paper that use the exercise to increase the blood pressure. You can see a clear decrease of the PTT and its correlation. And the other one is by the ice water stimulation. Yeah.
Yeah. Okay. Thank you very much.
So if you have any other questions, yeah. Okay, so if there's no more questions, then I will give the floor to the third speaker, Xu. Okay, so I will stop sharing. Okay, now it's your floor.
Can you hear my, can you see my screen?
Yes, we can see your screen.
Okay, so, yeah. Okay, let's start. So this is third part. I think Daniel and Wenjing to introduce our first two parts, focus on the camera-based contactless, the health care. This is third part. We focus on the wireless-based vital sign monitoring and also post-estimation. My name is Yu Wang from Florida International University, and also this is joint work with Professor Shu Mao, student Chao Yang, Ren Ze Huang, and Jamie Peto, Chara, and Tianya Zheng. Okay, so in my talk, I mainly review our the book, so special focus on the wireless part, and I will discuss the background, also mainly focus on the four technique: radar-based vital sign monitoring, acoustic-based, Wi-Fi-based, and RFID-based. Also, I discussed the future work. Okay, for the special for the Internet of Things-based healthcare, this is very important. We know we can use the different sensors like the camera, right? Also use smartphone, the other sensors as raw meter, gyroscope, and also we can use our wireless signal like the Wi-Fi, radar, RFID, acoustic, or smart, also smartwatch, different sensors to measure like vital sign signals like body temperature, heart rate, respiration rate, or blood pressure. And then we can, based on the gateway and also to over the wireless communication to transmit data to the data center. And also then we can synchronize to analyze that data, give feedback for the patient, or give that data to the hospital or the doctors to analyze it. This is very useful for BP monitoring or elderly monitoring. Okay, so in this part 3, we mainly focus on the wireless based vital sign monitoring. I think we need also discuss our new book and contactless vital sign monitoring. This book include 2 parts. And the first part work on camera-based vital sign monitoring and consider for the different vital sign applications, breathing monitoring, blood pressure, heart rate, or some applications. But in the second part, we focus on how to use the current wireless device, commercial device, or some special device to monitor the breathing rate, heart rate, or current recent paper also gives the potential to use like radar to monitor like the blood pressure or other vital signs. Okay, this some like the wireless device, for example, we can use a laptop to set up like Wi-Fi protocol to monitor like use Wi-Fi channels information to monitor the breathing rate, heart rate, and how this one that is the TI meter radar. We can use to with the large bandwidth to monitor like different vital signs. And also our work use like the RFID, the reader, and also antenna for the post estimation. Also use that to design variable-based vital sign monitoring. Okay, so from our textbook, this book, and also we introduce, we can use the different wavelengths, different like the signal to monitor that vital signs. For example, respiration, blood pressure, heart rate, SpO2, or temperature, body temperature. And most of the part we can see we focus on the camera-based. And sometimes most of our work in the wireless part focus on the respiration and heart rate. And recently some new work focus on like the blood pressure. Okay, what's the basic idea? We can use the wireless signal to monitor the breathing rate or heart rate. So that means we have one transmitter and one receiver. Transmitter can send a signal, and also that signal hits the person's body chest, and then reflect that signal, and the receiver can extract the signals. And this basic principle for the wireless-based vital sign monitoring depends on like movement-based, the tracking, vital sign tracking. So for the receiver, for example, this is look at radar, or this is smartphone, or this is RFID reader, any device, we can use this model. And from this part for wireless sensing, for receive, okay, signal, the phi r, that equals amplitude and including that phase. And because of that distance change, okay, when the chest, okay, that move, and we can see, we can capture that phase, okay, change. So the basic principle of wireless sensing is that the breathing movement leads to the change of received signal phase, for example, in this part. Okay, this table we review, okay, the different technologies and for the pros and cons, and use the different device or the features or some technique. And especially in this book, we discussed about like use the radar and use the Wi-Fi receive signal strengths. Okay, for example, use ZigBee, also use narrowband or Wi-Fi. Also currently use the physical layer Wi-Fi channels information. Also, we can use like as RFID reader, okay, to do that. And all we can use like acoustic, and we can use the smartphone-based acoustic, or we can consider the microphone array to do that. Okay, so for this is we easy to find there are different devices to support the like vital sign monitoring. And there are different, someone consider the low cost, someone with the high cost, someone just used commercial device, someone used a specific device to do this. Okay, so for this tutorial, and I think I need to go over special in the computer vision the community I introduced, okay, how to use the wireless special radar, RFID, Wi-Fi acoustic to monitor the breathing rate, heart rate, and also activity recognition, post estimation. I think next stage is how to merge that two domains knowledge, the camera-based or like a wireless-based to monitoring the value sense. Okay, first one I introduced about the radar-based value sense monitoring. I think 5 years ago, maybe it's very expensive to use radar to implement this experiment. And we need to use the accommodate, especially the hardware to design a radar. For example, we can design like there are 3 types of radar system. For example, continuous wave radar, or like the frequency modulated carrier wave radar, FMCW, or some use the ultra wideband radar. Okay, you know, currently, if you check out the current new the iPhone, like from I remember from iPhone like it's 11 to current iPhone 15, and Instone also have that UWB chip. Okay, this device, and like the Google's Pixel phone also have the FMCW, the meter wave, that is the radar. So next generation is that for the smartphone, you know, we have the camera, we have acoustic, we have the radar. Okay, so I think in the future there are some interesting work how to merge, how to design that to the multi-model that system. Okay, in this part, in the radar-based system, let's back here. I one by one to introduce, okay, what's the principle of each radar system? And this is also very important because if you know the idea or know how does it work for each radar technical, and then traditionally we can use this technical to design acoustic-based value sign monitoring on smartphones in our next part. Okay, first one I need to introduce about like is continuous wave radar. Okay, you can see like this name. Okay, that is the signal is not modulated. Okay, so just for example, we send that is one signal like with the cosine 2 pi ft. The frequency here is constant value, and we use this architecture. It's easy and look like that communication architecture, but the transmitter receiver at the same device. And based on this one, okay, we use transmitter to send that the signal, and also use receiver to receive that, and then fix that signal. Okay, goes through the ADC, and also we use signal processing, digital signal processing. Finally, we can get the breathing curve signals. And based on that, if we use FFT to see that in this figure, we can get the okay in this range near 80 beats per minute for that the respiration rate. And for receive signal, this is transmit waveform, and for the receive signal, we can get this. Also, the principle is similar. and because of the movement of chest, the phase will change. So this distance change lead to the phase change. If we gather the phase difference, and then we can extract that periodic signal for the breathing or for the heart rate. Okay, heart rate. Okay, second part, I think this is very useful, also very popular. Recent, I think 2 or 3 years. You know, special after the TI meter radar, someone called, okay, we into the AI radars area. Okay, because previously, I think 5 years ago, if we want to use radar for the vital signs, smart health monitoring for the, and we need to use, for example, USRP, and we need to get or develop our radar chip that are very expensive, also block that these applications. But current thing is, okay, we have like here meter radar, and also for this radar, some information. For example, there are 3 transmitter, 4 receiver, and also you can there is the data collection board. You can collect this data part. And before introduce this TI meter radar, first I can discuss about what is FMCW. Previously, I discussed the CW. CW is that is just we can say use the constant that frequency. Here is we need to modulate that frequency. If you try that figure, that frequency is modulate. Okay, you can see in one chirp, and from the minimal and frequency to the maximal frequency. And then we can, if frequency in this one chirp, that will linear increase. And finally, we can transmit that signal that is different from the CW. Okay, that radar. Okay, so based on that one, okay, so you can see this is nonlinear, and we transmit this signal. We generate this chirp and use antenna to transmit, and then that chirp is reflect of one object, for example, person chest, and then reflect signal is received at this one antenna, also receives the other antenna if there are 4 antennas. And then we use this mixer and to a special get, we call this is continuous frequency signals, AF signal, or get AF signal. And after that, we use the low pass filter to remove the higher frequency. And then we consider the ADC, analog digital transmission. And the last one is we use the fast Fourier transform to get a range FFT to estimate in this part, to estimate the distance. Okay, so this is the FMCW radar. Later I will give the 3 examples in our domain, the 3 top conference paper, how to use this TI meter radar to combine like the deep learning to design like to recover the vital sign signals. Okay, this is the FMCW. Okay, so here is basic. If you're interested in the how to use the TI meter radar, you can search TI meter radar tutorial. Okay, that gives you very detailed information how to use that. For example, in first there mentioned 3 stage, and I here just show 2, just for the vital sign monitoring. First step is that okay, we consider we can use the range FFT and for each of chirp, and then we can get this. For example, in this for each of the chirp we can get this this figure, and based on that one we call this axis. We call this the fast time. This fast time related with the distance. For example, based on this FMCW radar, we can estimate distance between the chest and this device. And the second part is that we want to see that vibration of that object. For example, like the breathing movement, vibration movement. But this is we need to see this. This is see this each row, and then focus on each of column, and we do the second FFT. We call this a Doppler FFT, and along this column, and then we get this. We call this Doppler FFT to get this velocity or like vibration. Okay, traditionally, okay, for example, we assume that there are 2 objects between the radar and the 2 persons. And so this is the range 4, for example, this 2 meters, this is 4 meters. And then we can focus on, we can separate these 2 users. For example, we just want to monitor the first user at the 2 meters, and then we can check out that the column and to see that vibration or this velocity. And if we check that, and then we can see for this person, based on this slow time here, the velocity, we call this slow time, and range is a fast time. Okay, based on this slow time, we can estimate this displacement or vibration of that chest. We can gather this to detect that respiration pattern. Okay, the last radar. Okay, this is also very popular. You know, current this radar is current use so many the smartphones, from the iPhone to current Samsung or other the smartphones. And for the ultra wideband, the idea is okay, we need to use the large bandwidth and to transmit that pulse or this pulse. And then also this signal also that the reflect on the chest, and the receiver can get this. And this time to transmit signal like the chirp. And for this one, you can see there delay for different the pulse. And then receiver also can get that signal. You can see there is offset. Okay, the time offset. And then okay, the receiver based on that mixer, we can estimate. It's easy to get estimate that that distance. Okay, based on this parameter. And you know, there is one commercial device, IR radar, and we can use that radar directly to monitor the breathing rate. Also use this radar for other application. Okay, for in the car, for the driver detection, or for the smart home, the monitoring. Okay, there are some challenge problem, research problem for the radar-based health monitoring. For example, how to recover the heartbeat waveform with radar. Okay, it's easy to get the breathing waveform, but the heartbeat waveform is challenged because this signal very small. Second one is that how to monitor vital sign signal, and special, for example, breathing monitoring in the dynamic environment. For example, I think our second part, when he introduced about how to use the camera to monitor that the user's heart rate under the fitness, the working. But use the radar system, or wireless system is very challenging. The reason is that the wireless signal to monitor vital sign based on the movement of the chest. So if we have another movement, for example, the walking, running, and I think this large movement definitely will influence that the small like breathing or heart rate movement. So how to recover based on the vital sign signal from the mixed signal. This is also challenge research problem. Another one is how to monitor the multiple user based on wireless signal, based on these mixed signals. And also how to monitor the vital sign and other activities continuously, how to design the deep learning radar, okay, the radar system, how to use deep learning to solutions. I think our first talk introduced the deep learning based, like a heart rate estimation based on camera. And how to improve the radar sensing range. Currently, someone just 7 meters, how to enlarge that range. And another one is combined current, like a 5G or 6G technique, how to design that radar backscatter to improve the robustness. And the last one is how to use deep learning radar for the other health monitoring, like human stress, motion, gait, sleeping, fatigue, pulse for detection. Okay, I introduced so many research problems here. I think I need to specially discuss about 3 applications, and from our one group from the Junro's group. And for this idea is also we can use the different radar. Special this group test that from the use the UW radar and also the FM7 radar. Also, you know, I think our first talk also discussed how to special use the self-supervised learning, okay, to improve the robustness or performance for the heart rate estimation with camera. Here is also give another solution. And can we use like also the deep contrastive learning and to perform like the blind signal source separation. You know, for the if we want to recover the signal, breathing or heart rate signal under some movement, the body movement or other like the working movement. So this mixed signal there is a nonlinear between the received signal and original value set monitoring. So solution is, can we use some deep learning, this nonlinear neural network to instead of that basic signal processing to handle that. Okay, traditional BSS assume that linear signal mixture, but the body movement, respiration, heart rate that is highly nonlinear. And so solution is we can use DCL to implement this nonlinear BSS. You can see the results. This is the received the radar signal. You can see this is not the clear breathing or heart rate signals. And the special in this moment, the type writing, and the writer part is working on the treatment. And so the second part is we show the breathing and special for the recurring or the baseline or the ground truth. And we can see for breathing is we will get very clear that similar that curve. And for these two cases, for heart rate also similar things. And you can see this is the recurring heart rate. This is the ground truth heart rate. This is the baseline. If we use the traditional signal processing solution, we cannot get the denoising clear the heart rate signals. Okay, I think this is also one first paper to introduce how to use the deep learning to address this issue, to separate signal under the movement, large movement like body movement, the type writing, and also published in the top conference paper in the SIGMOBile. And the second paper, this definitely previous solution we call the movie file, that is the cost is high. Can we have the alternative solutions? And this paper is second one. Focus on we first focus on the respiration monitoring, and the solution is previously that proposed like the DCL, contractive learning. Here is can we design like a variation autoencoder to design that how to recover that breathing curve. And the idea is that for the radar system, first we need to separate receive signal in the I path and Q path. These two parts. And then to design, we have the in-phase or conjecture I and Q encoder, and in the middle part we design this variation encoder and variation or autoencoder. And then finally we can want to recover the respiration curves. And if we want to use this solution, what's the basic idea? Definitely, this idea I think borrowed idea from Daniel's work. And I think Daniel gave the first work how to use the deep learning to recover that the heart rate signal, that vital sign signal based on the deep learning based on camera. And here is can we use the like radar to recover that? Definitely, also we have the contact PPG. This is not PPG. The contact the bear chat sensor as the benchmark. We need to have this label to train these models. And here is the results. You can see for the different movement, like the type writing, accessing, also working or turning over. And this solution, special based on IQ, BED, can recover that waveform. You can see in this red curve and blue curve is similar. And this is the just the phase-based, where include very large noise. We can use the deep learning radar to recover the breathing signal, values and signals. Can we use also publish in the ECM synthesis? Now is, can we use that similar solution to recover the heart rate, a small signal? And definitely also use a similar solution. We also have I in-phase conjecture, but design this variation encoder, and there is decoder part. And also there is this use the contact PPE as the baseline to give the labels to train that model. Finally, you can see this solution to compare with the other decomposition solution like the VED. And you can see this is the raw RF signal, just look like breathing signals. How to use that to recover the heartbeat waveform. And we use that special our labels to train that model. Finally, you can see This is the radar solution, UW radar. This is FMCW radar. And for the ground truth in this blue one, and also the this red here is also these solutions. And we can see the similar with that the baseline solution, and that you can see sometimes get very small amplitude for that the heart rate. Definitely, which lead to the high errors for the heart rate estimation. Okay, as I introduced about the radar-based vital sign monitoring and how to use deep learning to design the vital sign monitoring under the movement, especially the human movement. And I also introduced the other work. If you are interested, you can Google that. In this area, special TI-based meter radar, and we can use that radar. Okay, first, okay, some new work is previously we consider the body, the person is moving, for example, working or the typewriting. Another thing, if the transmitter, if there is movement, and how to remove that interference. And the second part, most of the work is how to use that radar to design some new vital sign application. The current work is we can use TI meter radar to recover, to estimate that the blood pressure. You search that current census paper last year. Okay, I introduced the second part. Okay, quickly introduce second part. First part, we introduced radar. Okay, radar current we use hardware to design like the FMCW or UWB or CW. And can we consider use software to implement like different radars modulations to design smartphone, smartwatch, or like a smart home based vital sign monitoring use acoustic? Okay, this is basic idea. For example, the basic one, we have the smartphone speaker and also microphone. And especially we can use the audio signal part from the 18 kHz to 20 kHz and to design this acoustic sensing. Okay, sense that acoustic signal, and also your microphone record that. First one is I introduced my one first work in this in this area. We designed the CW radar for the vital sign monitoring. And but also still some challenge in this area. We know if we use the CW radar, definitely we need to extract phase. Okay, based on that one, okay, we propose like the sonar beat system. This people work also got the best demo award in the good conference. And the solution is also, you can see, we use a smartphone, we modulate that an audio sound signal, we transmit, and also use microphone to record that. And then we design receive signal processing part. We get extract IQ demodulation, and but compared to radar, acoustic, that signal is very weak. So definitely we need to remove like the static vector, and then extract phase and for the vital sign monitoring. Here is our system design. First part, we detect that the signal arrival part. What's the beginning of the receive acoustic signal? You can see if we use the short-term phase transfer to detect that the beginning of the signal. Okay, there are very large signal power change. Second part is we for the signal processing part, and we need to extract I and Q. It's very easy, but based on the sampling rate, and we want to design the real-time that breathing monitoring. First, we do the down sampling, and then we use the transmit signal to demodulate that to get, and then use a low-pass filter to get the in-phase and quadrature I and Q. You can see this is the after process. You can see for the special for the I and Q part. And still, this is not the periodic breathing signal. And the second part is definitely we need to remove the stacked vector effect. We design the adaptive signal processing medium filter to remove that. After that, we can get the signal look like this, but still there are some jump signal, and we just unwrapped this, and then use the moving filter to remove some noise. We can get a very clear breathing, and this is estimate breathing rate. I think, okay, the main difference between the camera based and also the wireless based, or like this acoustic based, we can get very accurate breathing rate estimation. If you check the previous two talks, I think we get very good accuracy for the heart rate estimation. But for the breathing estimation, we can see the error, average error, as I check out that near the 1 ppm, okay, for the long range. But use the values based on the movement, on top of movement, we can guarantee that the error, so transition under the 0.5 BPM. Okay, we test this system with different smartphones, and we also neurolog respiration the belt as the benchmark. We test this system in the cinema, a very large interference for the sound interference part. And here is also in the office, in the lab, and we can get the better performance, and that median error is under 0.3. And we test the system, even though for the cinema scenario, we also can get the errors, mean estimate errors under 1.5. Here is our demo system. You can see this is benchmark based on the neurolog sensors, and this is smartphone, and our real time in the first 15 seconds we just collect data. Then we can real time or get this one window and real time to show that breathing waveform and use FFT to get that breathing rate. Okay, so let's show that. If you check that here, okay, this is system, okay, the BPM, and this is for the benchmark. You can see, you can count that number of the 8 peaks in the over the 30 seconds. So also like the system, the BPM, our accuracy is 16.04, so very good accuracy. And our recent work is previously we discussed use the CW to CW phase-based breathing monitoring, and also can we use another radar-based solution? Okay, can we modulate that signals? Use FMCW for the breathing monitoring. Another one is there are very good application is we consider the breathing control. Okay, so special for the these applications, we can estimate how long for the exhale, how long for the inhale, and we can calculate duration for this. And this is very useful for biofeedback for the respiration. And a similar architecture just from previous CW-based the modulation to current FMCW modulation. And also we propose the new, like the signal processing, for example, convolution, hearable transform, and calibrate that data. Here is our modulated signal. We currently focus on special, like the 15 kilohertz to like the, I remember 20 special 24 kilohertz, and that is a spectrogram. You can see we can modulate these FMCW signals, and then for the receiver, we based on our convolution and hearable transform, and we can detect. We have reference. We can detect that based on correlation, we can find in this part the breathing will movement have the movement, and so based on that one, we can see we can special track that you can see the breathing signal for the apnea for the stop breathing at the exhaling, and also stop breathing inhaling. You can see maintain that breathing, hold that breathing, and also we can monitor our breathing signal with the body movement, and also check out like the inhale and exhale estimation based on our solution for the respiration based biofeedback. Another one is, can we if we have like the current we have the earphones, right? Can we just passively to record that to get robustness breathing monitoring? And based on our current tool, we design our system. Okay, we consider to use just record signal and design our noise reduction and use a low pass filter EMD noise subtraction, and then to estimate that breathing. We use this solution, passive solution, and if you check these two demos, and we can, especially get the, so Okay, we can set our system based on, you can see here is the smartphone. Okay, this time this person is working. Okay, not just not rather than staying on the. Okay, based on this system, also we can get a robust breathing monitoring. And the right part is that if we, okay, special play the music. Okay, for these things, can we still recover that breathing signal in this interference part? Okay, we can also set up the system. Okay, in here. Also, because based on our signal processing, we can largely cancel or mitigate that inference of that outset or environment, that interference. Also, we can get very good breathing monitoring based on these two systems. Okay, this is our two demos. Okay, next thing is I quickly introduce about like the value monitoring based on Wi-Fi. You know, for smart home monitoring, I think every family we have like the house, we have like the Wi-Fi router, we have the laptop, we have smartphones. Every day we access the internet, we use Wi-Fi, commercial Wi-Fi. Can we use Wi-Fi for vital sign monitoring? I think also this is one type of work. Currently, we also have several citations in this range, in this area. And we propose face. Previously, there are also like radar based or like the Wi-Fi amplitude based. And can we use a face? Okay, what's the idea? Okay, what's the motivation of this idea? This is also like idea from previous like radar based. If we have the face, it's easy to extract that breathing waveform because the movement of like the chest, it's easy to track based on that the face part. And okay, in order to implement that one, we need to have the Wi-Fi interference card. And based on the receiver part, we can extract, we call that is channel state information. Okay, CSI. And for the CSI, if we want to use the face, use amplitude, that's fun. But use face, there are several offset errors. For example, down converting, sampling, packet detection, face lock loop. And you can see this in mirror face, there are some offset. The good thing is that for the same memory card, all these offset that is same. So based on this assumption, it is easy to calibrate that. We use the two antenna, we get the phase difference. Then we can get use this phase difference to monitor that breathing signal or heart rate signal. You can see previous are just the basic phase. If we do the phase difference, and you can see the right special right dots focus on one area, this is stable. Okay, on top of that motivation or assumption, we propose this our current work, and we propose use the CSI Wi-Fi CSI based Wi-Fi CSI based breathing monitoring and heart rate monitoring, and also including like signal processing. And then we use wavelet to separate that for the breathing rate estimation, heart rate estimation. But before monitor the breathing rate, we first need to use the energy detection for the environment, special for the environment detection. And we just consider, there is no person, there is person working, standing up, or there is the person in this room, sitting in the room. So for this case, we can see there is periodic signals. Then, for on top of the received signal, we need to remove this is original phase difference. We need to remove the DC component. And also we need to remove the high frequency noise. Downsampling, we finally get this curve. And after that, because Wi-Fi, if you have background for the communication, Wi-Fi use OFDM MAMO system. We have the use special for OFDM, we have multiple subcarrier. So that gives the more dimensional to choose that subcarriers. So another thing is, if someone imprint these slides, you can send me the email. So another way is we can use how to choose which subcarrier. We need to choose that most sensitive that subcarrier based on the absolute deviation. You can see this is largest value. We can choose the top 3 and get a median value in this part. This is very clear periodical breathing signals for this one. Okay, so then we use the discrete wavelet transform. This original signal, we can get the denoised green signal very clear. And also we based on that the heart rate range, frequency range, and also based on the component 3 and component 4, we can combine that to get reconstruct heart rate signals. Okay, and then for the single person, we use peak detection to do that. For the multiple person with monitor, we use the room music. And for the heart rate estimation, we just use FFT. And this is our system setup. And also, this is one PhD student, we collect that data. You can see our system can monitor breathing rate up to like 10 meters. And also through the wall, you can see here is this is the receiver, this is transmitter person here. Our receiver can monitor us breathing signals, okay, in the lab. Okay, for this is corridor office and through wall scenario. And if let's see the performance. For the phase speed, we can get also the median error that estimated error is under 0.3. And for the heart rate, okay, we can get a similar error like near the 1 BPM, like the camera-based solutions. And we also test our system, especially in the MRI, that scenario. This is very challenging. I can show that, especially, okay, the person inside here, and our device, okay, deploy in this room, and we remote to control that. Okay, this is also contactless value monitoring. Wireless also can through that device and capture the movement of the chest. And this can help for that MRI imaging, okay, for as a trigger for this. Okay, traditionally for MRI, we need to take picture, we need to hold the chest, but this time our PCB system can help do that for this system. And okay, another one is also we propose, can we use wireless to special at smart home for the multiple user, for example, up to 5 user subject receive monitoring. I think this is so challenge and for the radar of other systems, smartphone, maybe for the camera. But this is, I think, the first paper, we designed the system based on the tensor decomposition. We use the Wi-Fi OFDM memo system. We created we call this, you can see, use multiple subcarrier, and also to each subcarrier, we create that anchorization. And then we can get our special, the anchor matrix. We do the CP decomposition. And if you know the number of users in this room, finally, we can specially to design the auto correlations, do room matching, and to get our signal, and then fuse our signal based on peak detection to detect that. You can see if there are 3 persons in the room, and if you use Wi-Fi, you can see in the last part, red part, the signal become very weak, and because there are 3 persons. And 1 person is easy to extract that. But if you use our solution, tensor decomposition, we can maintain that accuracy, special, you can see under special median accuracy under 0.3 up to 5 persons, very challenging area, and use our solutions. So if you are interested, you can read this paper. Okay, so let's discuss our last topic. Last topic, we focus on RFID. And also currently also we have grant to mainly focus on this part. Compared to Wi-Fi, there's some advantage of the RFID. First one, for RFID, we have the RFID tag. So this look at variables. Another one is also we can use the wireless signal to receive that. And also RFID tag also very cheap. And another one is RFID tag mitigate some interference for the environment movement. For example, another person working in this same area, and this solution is better than the previous, like radar-based or Wi-Fi-based solution. Okay, similar solutions. We deploy that the RFID tag on that clothes of this person, and then we use the reader to extract that feature. For example, this reader, commercial reader, also can report that the RFID face information. This face information we can see also including that the distance part, and also the 3 offset error. And the first 2 error regarding RFID transmitter and receiver antenna, and the last error related with tag, that the antenna. So based on that one, okay, especially in US, in order to mitigate that the collision, okay, we consider 50 channel the hopping is standard for the RFID protocols. You can see there are 50 channels and over the 10 seconds that jump. And based on this protocol, you can see, can we directly use that raw RFID face data? You can see this data is raw, very random, including that special offset, okay, for this part offset. And especially you can see each of the channel Fi will change, definitely lead to the face will change. So can we cancel that or calibrate that? It's easy to design that. So the solution is, basic idea is we can map, if there are 50 channels, we can map the other channel's face to the first channel. Okay, and then we just monitor the first channel, then we can mitigate that the frequency offset. Okay, solution is we can cancel that frequency offset. Okay, multiply this Fi over Fi plus 1, and then we just map from the channel I plus 1 to map to channel I, and it's easy to estimate that, get average, get the difference, and then the next channel just minus this difference to recover. You can see this brown one, we can recover the same channel, that means same frequency. And based on the previous raw face data, if after the calibration, we can get this our periodical breathing signals. And also we can use that for the apnea detection. We design our system. We also have multiple tabs. We have the movement detection, DC removal, tab detection, downsampling, and also we design one neural network. Okay, this is first introduce signal processing. You can see after frequency hopping offset mitigation, we can get this one. And after the DC removal, all the signal that is the focus on the zero of the phase. And after that, we use Hampler filtering and to remove, and a low pass filter to remove that the high frequency noise. We get this recurring breathing signals. And for apnea detection, I think how to detect apnea, this is challenge. The challenge part is how to collect that data for the apnea. So the solution, how to mitigate, how to avoid this. We propose new solution. We train that normal data, because breathing signal is easy to train. And like this. Well, solution is we can consider to propose the unsupervised solution. I think like the current work from the radar-based like the breathing heart rate estimation. Also, we propose variation autoencoder, and we recover our breathing signals. And then we can just, based on this one, to calculate that KL divergence. And then to compare with threshold and to find, okay, the larger than this, that means a large difference for the receive signal, our this threshold, and we consider the apnea. And also smaller, we consider normal respiration. You can see this is experiment setup. And for this is RFID reader, this is China, the multiple, like the 5 tags. Okay, we test means also in the same scenario and compare with this baseline. You can see based on this solution for the 2 scenarios, we also can get very good breathing rate estimation, and also under near the 0.1 that BPM. And another one, okay, last part. If you're interested, you can check my webpage. In this area, also we use RFID. This is just first work. Also, we use this idea RFID-based vital sign monitoring. Use that for the driver fatigue detection. This is second work. Third work, also we use RFID tag for the breathing monitoring under the driving. Okay, this is look like the previous paper, how to monitor the breathing rate, heart rate under large movement, especially in the driving environment in this case. And this also, that work also got the best journal paper award. And recent also we focus on, okay, like human activity recognition, all the pulse estimation, you know, special current like the AR, VR, right? When we have that needs that pulse estimation. Can we use the RFID to implement that, these solutions? For pulse also can use for the gait recognition for some other hair-based detection. For this part, we have the multiple tag on the body or to the body. And but this solution is called how to merge like the camera and special the RFID tag. So the solution, Another one is that how to design privacy preserving solutions. That means if you use camera, definitely that expose that privacy issue for this person. Our solution is we just use Kinect the camera of at the training part to get a label for that data, RFID data to train. But the online test, we remove the camera. We just have this RFID the radar antenna for the real-time post-estimation. This is our design. Our solution is we first offline to train that model, and we have several data pre-processing. We also create a tensor, and we design that the deep kinematic neural network to predict that the post structures. And camera just for offline to help that for the labels of the joint points. And here is our for the different that posts. And here is you can see the ground truth based on camera. This is based on RFID, okay, without camera. And we can get the same tree of the post estimation. Okay. And also here is also we have the different activities for the post estimation, okay, for the scratching or for the other one. And last one is also we test our system for the different lab, corridor, living room. We can maintain our estimation error is under 5 centimeters for the post estimation. Okay, let's summarize this third part work. I think first, I give the background for the wireless-based vital sign monitoring, and then I introduce about 4 types of technologies for the vital sign monitoring. First one is radar-based. So I introduced for CW radar, FM CW radar, and UW radar. And on top of that one, I give the basic challenge or open research problem on top of the radar-based. I mentioned that 2 years ago, we into the AI radar area because currently we have our smartphone have radar, UW radar, and FM CW radar. Also, we have very, I think, certified or cheap radar device, commercial radar device. We can use that for the health monitoring. And the second part is I introduced the radar modulation, okay, FM CW radar and CW, and how to use CW and FM CW to design acoustic-based sensing for the breathing monitoring or for the respiration biofeedback, and use these two solutions. How to use that passive acoustic for breathing monitoring under the movement, under the interference with the sound. And the third part, I introduced, okay, every we use Wi-Fi to access internet. And we use Wi-Fi special OFDM memo system, Wi-Fi based, CSI based breathing heart rate estimation for the single person, for the multiple person, up to 5 persons breathing monitoring. I introduced phase speed, TensorBeat. Also, we have other like ReSpeed or merge multiple model solutions in this area. And also current, we also have ongoing work is how to merge like the remote PPG, I think our first or second topic, and this Wi-Fi based, CSI based vital sign monitoring to improve the robustness for the breathing and heart rate estimation, okay, in this stage. And the last one is introduced about RFID based vital sign monitoring, introduced about, okay, include RFID reader, antenna or tags, and how to use that, how to calibrate the RFID phase and use this for the value breathing monitoring, and also give the one solutions variation autoencoder for the unsupervised apnea detection. Last one is introduced about we can use the camera as the give a label for the RFID. We can implement this 3D post estimation. I think also new direction in this area. In the future, also we need to continue to working on the robustness wireless health monitoring in the dynamic environment for working or other fitness or like other environment dynamic. And second part is, we can use current like smartphones, the iPhone 11, 12 up to the 15 and a commercial device, and to extract that feature to design that vital sign monitoring or some other applications. And also use like the TI meter radar or Wi-Fi chips, new chips. Current, I think I discussed that Wi-Fi chip just 802.11n, but currently we also can have used actually 802.11ax or AC or next generation like the BF, ISAC, or Wi-Fi 6E, new router, we have, because for the new standard, we have large bandwidth, we have the higher resolution, similar with radar for this. And also previously, I just introduced for the smartphone-based acoustic-based vital sign monitoring. Also currently, also we have the submit paper focused on the microphone array. We for example, we have 6 microphone array, and then we can do beamforming and to increase that range between the object and this device. For example, currently we have the Google Home, right, Alexa Note. For this one, can we use this device to monitor the breathing, heart rate, or other activity related health? I think also that's very interesting. And for the long range backscatter, for this one is short range RFID backscatter and consider long range. Another one is how to merge that, the different. I think, for example, Wi-Fi or like a special radar, and they have the advantage, for example, work in the dark area at night. But if we consider camera based, that become performance become weak. Okay, because it's special at night. Can we mitigate? Can we combine that two techniques together? Design this multimodal, cross-modal sensor fusion of this wireless based on wireless and camera together for design next generation vital sign monitoring, and also how to design new deep learning AI radar and also new wireless sensing design. And I just introduced mainly focus on the breathing monitoring. And definitely, I mentioned that this year there is one paper used the meter radar for the blood pressure monitoring. And can we validate other solution, use a multimodal to improve that performance? I think our special second talk discuss a lot of solution. Just use the camera for blood pressure measurement. Can we use that multimodal to do this? And body temperature, okay, some sensors for the body temperature, or some other for special use for the special AR, VR for the stress, emotion, or we consider the gate-based monitoring. Okay, and another one is if we have gathered that breathing signal or curve, can we use that for the disease detection? For example, for the long-term COVID monitoring, for the lung function monitoring, or gate-based Parkinson monitoring, or for some other application. I think that also very interesting. Okay, thank you. So I finish my talk. Any questions? Okay, there is question from the chat. So I think the question is the UW radio in the iPhone 32X radar. Definitely, I think last month, if you check out the UBCOM conference, there is one paper from the Peking University to show, validate current the iPhone UWB, that chip can use that for the vital sign monitoring. You know, if you check out the library from the iPhone, special the Apple that tools, you can find that it give the special tool to estimate the distance or basic feature rather than the physically feature. And I mentioned like face. But if you use that the clearly feature, the distance angle, we still can use that feature for like the radar. You can see the distance angle like the radar. And if we have the distance angles, we can use that for the gesture recognition, activity recognition, or that breathing monitoring for this. I think you can special check out that paper. If you are interested, I can tap on this group chat about the paper for the UW radio in the iPhone. Any other questions? Any part we can discuss. Any technique for if you are interested, in the multimodal or vision based, anyone?
Hi, may I ask a question? So I'm wondering for the radar part, so say if the person wearing very loose clothes, and then the clothes will affect the say respiratory rate monitoring.
You mean the clothes also that can absorb that the radar system,
Yeah.
but the current system validates that because this special radar system or body system that can through that body, and also we can track some reflection, but definitely can through that the different clothes for this system. I think this is the different from like special the camera based, right? And also, I think I showed one. My work is we can use like Wi-Fi or radar to monitor like the breathing waveform through the wall. Definitely, we can through the different clothes analysis. Clear? Oh. Any other questions?
Yeah, I was wondering if there are two people in the same bedroom, right? They're lying next to each other on the bed. If it is possible with the Wi-Fi sensing to pick up the two different breathing rates. You know, how confined are the Wi-Fi signals, right? Are they bleeding over to the other side of the bed?
Can you repeat the question again? You mean the different person if the same room?
You have two people in the same bed, in the same bed.
Yes,
okay?
yes.
And you do Wi-Fi sensing, you have one device, one Wi-Fi device on the left side of the bed, the other Wi-Fi device on the right side of the bed.
Yes.
Can you then distinguish the breathing rate of both?
Yeah. So I think we proposed that if you check our face beat and also tensor beat. Okay, for the Wi-Fi receiver, for example, we use the laptop as a receiver, and there are two persons in the same room and are different to the breathing rate. For example, one is 0.3, another is 0.2. The hertz, I mean, for that. And for receiver, Wi-Fi receiver can get a signal that is the mixed signal, right? So for the mixed signal, for the multiple user estimation, definitely we need to consider special. I think in our paper, first paper is just a 2 user. It's easy to use like root music. It can separate these signals. And if we consider multiple user, like up to 5 users in this challenge scenario, we need the more features. We use the multiple antenna, multiple subcarrier to create the tensor, and then use powerful like signal processing, like the tensor decomposition. Finally, we can separate that signal, make signal into the 5 periodic signal. Okay, so then we can monitor this.
Thanks.
Okay, any other questions? Okay, so I think our time. Okay, we just also use 3 hours and a half now. Okay, we are close. If any question, you can email me and also Wenjing and Daniel and focus on this. I sent the 3 parts, and the special first 2 parts is camera-based, and the last part is current wireless-based. Okay, let's summarize in this tutorial. And I think the first part, and Daniel gave that tutorial, especially introduce his current work and how to use the learning solution, special deep learning, and for the special vital sign monitoring, signal recurring for heart rate estimation. This is very interesting if you check his work. And also, I think I remember one interesting paper is to propose unsupervised solution, self-supervised solutions to use unlabeled data to improve that performance. And this is the first part. And our second part is when you introduce the background of the remote PPG for the vital sign monitoring, and also introduce about the basic signal processing solution, the BSS, Chrome, or other solutions. And a special, second part, Wenjing also introduced about the clinic-based, okay, use the camera for the different applications, sleeping monitoring, heart rate, blood pressure monitoring, or the heart rate vibration monitoring. So many interesting work. If you are interested in that, you can check out Wenjing's webpage to see the papers. I think I summarized my third part is wireless part, and introduced that the 4 technique: radar, Wi-Fi, RFID, acoustic, and each technique then have the unique feature, like specific device. And you can choose one or merge two, or merge the camera and the wireless scatter for the vital sign monitoring. And in the future, maybe you can consider all the other applications. I mentioned that, like the stress monitoring, emotion monitoring, or like the lung function monitoring, or like the heart rate vibration monitoring based on the wireless these domains. Okay, so I think I finish here. Okay, thank you for joining this tutorial. I think this is also the hybrid tutorial, the first time we have the 2 online and 1 in person this tutorial. Okay, thank you all. Okay, maybe next year we all are in person to discuss this domain. And also I encourage you to attend Wenjing's workshop tomorrow. Okay, any question? No question, let's finish here. Okay, bye-bye.